In the vast darkness of space, orbits one small world that we call home. But beyond our sun lie trillions of stars, and orbiting those stars are worlds beyond imagination. Some scorching hot, some frozen solid, and even some that might harbor life. Welcome to Stellar Worlds, where we explore some of the most fascinating planets in the universe. Are you ready? Let's begin. For our first planet today, let's take a look at the restless giant, WASP 104b, the evolution of hot Jupiters. 466 light-years from Earth, in the constellation Leo, orbits a planet caught in the act of transformation. WASP 104b, a gas giant more massive than Jupiter, orbiting so close to its star that it completes a circuit every 1.75 days. This planet is not stable. Its orbit is slowly changing, shaped by tidal forces from its star. Its atmosphere is heated to 1,700 Kelvin, hot enough that molecules break apart, metals vaporize, and powerful winds reshape the planet every few days. WASP 104b is evolving before our eyes, offering a window into how hot Jupiters change over cosmic time. Every hot Jupiter we study teaches us something unique about planetary formation, migration, and evolution. WASP 104b's story is one of dynamical change, a planet whose properties today differ from what they were millions of years ago and will differ again millions of years hence. By 2014, the wide-angle search for planets had been operating for over a decade, discovering dozens of hot Jupiters. The survey's systematic approach, monitoring the same stars night after night across multiple observing seasons, was designed to find planets with periods ranging from days to weeks. WASP 104 was cataloged as a magnitude 12.9 star in the constellation Leo. Between 2006 and 2012, Super-WASP North observed this field repeatedly. The automated pipeline detected periodic transits every 1.75 days with a depth of about 1.2%, indicating a large planet, roughly Jupiter-sized, in an extremely close orbit. The signal was consistent across multiple seasons, ruling out instrumental artifacts or stellar variability. The transit signature was unmistakable. Every 42 hours, less than 2 Earth days, the planet crossed in front of its star, blocking a small fraction of light for about 2.5 hours. The regularity and consistency marked this as a high-priority candidate for follow-up confirmation. Confirming WASP 104b and measuring its mass required precision radial velocity observations using some of Europe's finest telescopes. We used the Corley spectrograph at La Silla Observatory and the Sophie spectrograph at Haute Provence Observatory to measure WASP 104's radial velocity, the star's wobble caused by the planet's gravity. The wobble amplitude was substantial, about 250 meters per second, confirming a massive planet. After careful analysis accounting for stellar activity and systematic effects, we determined a planetary mass of approximately 1.27 Jupiter masses. Combined with the radius of 1.14 Jupiter radii derived from transit observations, the density calculation yielded approximately 0.85 g/cm superscript 3, somewhat lower than Jupiter's 1.33 g/cm superscript 3, indicating moderate atmospheric inflation from stellar heating. High-resolution imaging with adaptive optics ruled out nearby stellar companions. Spectroscopic analysis characterized the host star's properties. By late 2015, all evidence converged. WASP 104b was confirmed as a hot Jupiter orbiting a relatively bright F-type star. WASP 104 is an F-type star, hotter, more massive, and more luminous than our Sun, creating an intense radiation environment for any close-orbiting planet. WASP 104's youth and high mass are significant. Young stars rotate faster, have stronger magnetic fields, and show more activity, flares, spots, chromospheric emission. This affects the planet through enhanced UV and X-ray radiation, stronger stellar winds, and variable radiation levels. The star's higher mass also means it will evolve more quickly than the Sun, eventually expanding and potentially engulfing the planet billions of years from now. WASP-104's stellar activity presents both challenges and opportunities for studying its planet. Stellar spots and faculae, bright and dark regions on the star's surface, affect transit observations. When the planet crosses a star spot, the transit appears slightly deeper. When it crosses a bright region, the transit appears shallower. By carefully analyzing these anomalies, we can map the star's surface features and understand stellar activity cycles. But this same activity complicates atmospheric characterization. Stellar variability can mimic or obscure atmospheric features in spectroscopic observations. The stellar activity also affects WASP-104b's atmosphere directly. High-energy radiation, UV and X-rays, heats the upper atmosphere, drives photochemistry, and can cause atmospheric escape. Understanding the stellar environment is crucial for interpreting the planet's atmospheric properties and evolution. WASP-104b is classified as a hot Jupiter, a gas giant orbiting close enough to its star that it experiences extreme heating and tidal forces. WASP-104b is interesting for its combination of high mass and moderate inflation. At 1.27 Jupiter masses, it's more massive than typical hot Jupiters, which tend to resist inflation due to stronger self-gravity. Yet it still shows 14% radius inflation compared to Jupiter. The equilibrium temperature of 1,700 K places it in the upper range of hot Jupiters. Hot enough for interesting atmospheric chemistry, but not so hot that all molecules are destroyed. With an orbital period of just 1.75 days, WASP-104b completes an orbit faster than most hot Jupiters. Only a few dozen known planets orbit this close to their stars. Very short period planets like WASP-104b are especially valuable for studying tidal evolution. The tidal forces, which depend on the inverse cube of the orbital distance, are enormous. These forces dissipate energy, causing the planet to lose orbital angular momentum and spiral inward. Over millions of years, WASP-104b's orbit is changing. It's either spiraling toward eventual destruction or, if tidal forces in the star dissipate faster than in the planet, it might be slowly moving outward. Long-term monitoring of transit times could reveal this evolution. The short period also means WASP-104b is an ideal target for repeated observations. Professional and amateur astronomers can observe multiple transits per week, building up extensive datasets that reveal subtle features in the transits and atmosphere properties. WASP-104b's moderate inflation, 14% larger than Jupiter despite similar composition, requires explanation. Several mechanisms contribute to hot Jupiter inflation. Stellar irradiation heats the atmosphere, causing it to expand. For very close planets like WASP-104b, tidal heating from orbital circularization or residual eccentricity adds internal heat. Ohmic dissipation, electrical currents generated by atmospheric winds interacting with the planet's magnetic field, deposits energy deep in the interior. WASP-104b's moderate inflation suggests these mechanisms are active, but not as extreme as in the most inflated hot Jupiters. WASP-104b's relatively bright host star and large planetary size make it accessible for atmospheric studies through transmission spectroscopy, analyzing how the planet's atmosphere absorbs starlight during transits. Transmission spectroscopy measures the planet's apparent size at different wavelengths. Molecules in the atmosphere absorb specific colors of light, making the planet appear larger at those wavelengths. For WASP 104b, observations with Hubble's WFC-3 and ground-based instruments have provided evidence for several atmospheric constituents, though clouds or hazes complicate the interpretation. Observations of WASP 104b have detected or inferred several atmospheric components. Key atmospheric findings: water vapor. Evidence for water vapor absorption features in the near-infrared spectrum around 1.4 microns. The signal is present but somewhat muted, suggesting partial obscuration by hazes or clouds at higher altitudes. Sodium, Na, and potassium. Tentative detections of alkali metal absorption in the optical spectrum. These metals exist as free atoms at WASP 104b's high temperatures and have strong absorption lines, though the observed features are weaker than cloud-free models predict. High-altitude hazes or clouds. The muting of molecular features and the spectral slope indicate the presence of high-altitude aerosols, either photochemical hazes, complex organic particles, or submicron cloud particles that scatter light and obscure the deeper atmosphere. Hydrogen and helium. Dominant atmospheric constituents, as expected, inferred from mean molecular weight calculations, though not directly detected spectroscopically. Possible carbon monoxide. Expected to be present based on equilibrium chemistry at 1,700 K, though direct detection requires high-resolution spectroscopy beyond current observations. WASP 104b's atmosphere shows the characteristic signature of partial cloud or haze coverage. Water vapor is present, definitively detected, but the amplitude of the spectral features is reduced compared to cloud-free models. This tells us there's a layer of aerosols at high altitude scattering light before it can probe the deeper, molecule-rich layers. Understanding the composition and distribution of these aerosols is key to fully characterizing the atmosphere. Clouds and hazes are ubiquitous in hot Jupiter atmospheres, yet predicting their properties remains challenging. At WASP 104b's temperature, 1,700 K, we expect several types of aerosols. Silicate clouds composed of vaporized rock can condense at specific temperature pressure levels. Metal oxides like aluminum oxide or magnesium silicate might form clouds. And photochemical hazes, created when UV radiation breaks apart methane and other hydrocarbons, produce complex organic molecules that accumulate in the upper atmosphere. The challenge is determining which aerosols dominate and how they're distributed. The aerosols aren't static. Atmospheric circulation, powerful winds transporting gas and particles, affects cloud distribution. Clouds might be patchy, concentrated on the night side where temperatures allow condensation, or confined to specific pressure levels. The three-dimensional structure complicates interpretation of one-dimensional transmission spectra. While transmission spectroscopy probes the atmosphere's limb, eclipse observations measure thermal emission from the planet's day side, providing complementary information about temperature structure and heat distribution. Spitzer observations at 3.6 and 4.5 microns during WASP 104b secondary eclipse detected the planet's thermal emission. The brightness temperature, derived from the infrared flux, is consistent with dayside temperatures around 2,000 to 2,200 K, slightly hotter than the equilibrium temperature. This suggests moderate heat redistribution from day to night, with the dayside retaining more heat than would occur with perfect circulation. WASP 104b's atmosphere is in constant, violent motion, driven by extreme day-night temperature contrasts and tidal locking. Our circulation models for WASP 104b predict strong eastward equatorial jet streams reaching 4 to 6 kilometers per second, supersonic winds that transport heat from the 2,200 K day side toward the cooler night side. These jets create a hotspot offset eastward from the substellar point by perhaps 20 to 30 degrees. Vertical motions, updrafts on the day side, downdrafts on the night side, create complex three-dimensional circulation patterns that affect temperature, composition, and cloud distribution. The efficiency of heat redistribution, how much heat is transported from day to night, affects the planet's overall energy balance and observable properties. WASP 104b shows moderate redistribution. The night side is cooler than the day side, but not as cold as it would be without atmospheric circulation. WASP 104b presents dramatically different conditions across its surface. The day-night contrast drives everything: the winds, the chemistry, the cloud formation. Gas heated on the day side expands and flows toward the night side, where it cools, contracts, and flows back at depth. This overturning circulation mixes the atmosphere vertically and horizontally, transporting heat and chemical species. It's a dynamic, constantly churning system unlike anything in our solar system. One important question about WASP 104b's atmosphere is whether it exhibits a temperature inversion, a layer where temperature increases with altitude rather than decreasing. Temperature inversions are caused by molecules or aerosols that absorb optical and UV radiation high in the atmosphere, heating that layer. Candidates include titanium oxide, vanadium oxide, or certain types of hazes. WASP 104b's temperature, 1,700 K, is in a range where these species could exist. Eclipse observations show thermal emission consistent with a possible weak inversion, but more detailed observations, particularly with JWST, are needed for confirmation. WASP 104b orbits so close to its star that tidal forces dominate the system's dynamics. Tidal forces arise because the star's gravity is stronger on the planet's near side than its far side. This creates bulges in both the planet and the star. As the planet orbits, these bulges rotate, dissipating energy through friction. This dissipation removes energy from the orbit, causing the planet to spiral inward. For WASP 104b, at 0.0295 AU with a 1.75-day period, tidal evolution is rapid on astronomical timescales. The timescale for significant orbital change depends on the tidal quality factors, how efficiently the star and planet dissipate tidal energy. If stellar dissipation dominates, the planet spirals inward and will eventually be destroyed. If planetary dissipation dominates, the orbit might actually expand slightly. Long-term transit timing observations could reveal which process dominates by detecting orbital period changes. Tidal forces don't just affect the orbit, they heat the planet's interior. As tidal bulges rotate through the planet, friction generates heat deep in the interior, similar to how flexing a piece of metal heats it. For WASP 104b, with its very short orbital period and proximity to the star, tidal heating could be significant, potentially contributing several percent of the planet's total energy budget. This additional heat source helps explain the moderate inflation. The planet is slightly larger than stellar irradiation alone would predict. By measuring transit times with high precision over many years, astronomers can detect subtle changes in the orbital period that reveal tidal evolution or the presence of additional planets. For WASP 104b, we've monitored transits using ground-based telescopes and space-based facilities. So far, transit times show no significant deviations from a constant period. The orbit appears stable on year-to-decade timescales. But tidal orbital decay for a planet this massive happens slowly, requiring decades to centuries of observations to definitively detect. Continued monitoring is essential. WASP 104b is one of over 400 known hot Jupiters, each contributing to our understanding of this diverse planetary class. Hot Jupiters span a huge range of properties. Masses from 0.1 to 10 Jupiter masses, radii from 0.7 to 2.0 Jupiter radii, temperatures from 1,000 to 4,000 K. WASP 104b, with its high mass, moderate inflation, and very short period, occupies an important region of parameter space. Studying planets across this range helps us understand how formation conditions, stellar properties, and orbital evolution shape planetary properties. WASP 104b, like all hot Jupiters, did not form where we find it today. WASP 104b formed in the outer protoplanetary disk, several AU from the star, where temperatures were low enough for ice to condense and gas accumulation was efficient. After forming, it migrated inward, most likely through Type II disk migration. Gravitational interactions with the gas disk caused it to spiral toward the star. The nearly circular orbit suggests smooth migration rather than violent scattering. After the disk dispersed, tidal forces from the star circularized any residual eccentricity and tidally locked the planet's rotation. The James Webb Space Telescope promises to revolutionize our understanding of WASP 104b's atmosphere. JWST's infrared instruments can observe WASP 104b from 0.6 to 12 microns with sensitivity and resolution far exceeding Hubble or Spitzer. We'll detect molecules definitively: water, carbon monoxide, carbon dioxide, methane if present, potentially metal oxides or sulfur compounds. We'll measure abundances precisely, map temperature structure, characterize aerosol properties, and search for weather variability. WASP 104b is an excellent JWST target. Bright star, large planet, accessible from both northern and southern hemispheres year-round. Planned JWST studies. Transmission spectroscopy. Detect and quantify H2O, CO, CO2, CH4, characterize aerosol properties, measure metallicity. Eclipse spectroscopy. Map dayside temperature structure. Detect thermal emission from molecules. Confirm/measure temperature inversion. Phase curves. Monitor brightness throughout orbit. Map 3D temperature distribution. Measure heat redistribution efficiency. Time series observations. Search for atmospheric variability. Detect weather patterns. Monitor cloud evolution. 466 light-years from Earth, WASP 104b continues its relentless orbit. Every 42 hours, every 1.75 days, it completes another circuit around its bright star, a journey that takes less time than a weekend on Earth. The planet is not at rest. Tidal forces stretch it into an egg shape, dissipating energy, gradually changing its orbit. Supersonic winds race through the atmosphere at kilometers per second. The day side bakes under intense stellar radiation while the night side cools. Every moment, the atmosphere circulates, chemistry evolves, clouds form and dissipate. Imagine approaching WASP 104b, if such a thing were possible. The star dominates the sky, brilliant and enormous. The planet glows orange-red from its own heat, thermal radiation from an atmosphere heated to 1,700 Kelvin and beyond. Descending into the atmosphere, you encounter the haze layer, photochemical particles suspended in the thin upper atmosphere. Below, the temperature rises rapidly. The winds are beyond comprehension, supersonic jet streams that would tear apart any spacecraft. Lightning might arc through the clouds, discharges far more powerful than Jupiter's storms. Thousands of kilometers down, the atmosphere transitions from gas to supercritical fluid, then to liquid metallic hydrogen under crushing pressure. And somewhere deep below lies the core, rock and ice, the original seed around which this massive planet formed. WASP 104b reminds us that planets are not static. They form, migrate, evolve. Orbits change. Atmospheres respond to stellar radiation. Tidal forces reshape worlds over cosmic time. The planet we observe today is different from what it was millions of years ago. And millions of years from now, WASP 104b will be different still, perhaps with a smaller orbit, a thinner atmosphere, altered properties we can only model but not yet observe. WASP 104b teaches us that understanding planets requires understanding not just what they are, but how they change. That every hot Jupiter is caught at a specific moment in a long evolutionary story. That to truly comprehend these worlds, we must think in timescales of millions and billions of years. This is WASP 104b, the restless giant, a massive hot Jupiter in rapid orbit. A world whose atmosphere churns with supersonic winds, whose orbit evolves under tidal forces, whose properties change on cosmic timescales. A reminder that planets are dynamic, that the universe is in constant flux, and that understanding these distant worlds requires patience, precision, and the recognition that what we observe today is merely one frame in a much longer story. The observations continue. The planet orbits on, restless, evolving, and slowly, measurement by measurement, we uncover the secrets of hot Jupiter evolution. Next, let's head on over to LHS 2665b and the promise of habitable super-Earths. Just 59 light-years from Earth, practically in our cosmic backyard, orbits a planet that might be habitable. LHS 2665b, a super-Earth roughly twice our planet's mass, circles a small red dwarf star every 48 days, positioned within the habitable zone where temperatures could allow liquid water to exist. This planet was found not through transits visible from Earth, but through the subtle wobble it creates in its star's motion, a radial velocity signal discovered by patient, precision observations over many years. LHS 2665b doesn't transit from our perspective, making atmospheric studies more challenging. But its proximity, its location in the habitable zone, and its super-Earth mass make it one of the most intriguing targets in the search for life beyond Earth. LHS 2665b represents the kind of world that might be common throughout the galaxy, a super-Earth around a red dwarf, the most numerous type of star. If such worlds can support life, the universe might be far more inhabited than we ever imagined. The High-Accuracy Radial Velocity Planet Searcher, HARPS, is one of the world's most successful planet hunting instruments. Since 2003, it has discovered hundreds of exoplanets by measuring the tiny wobbles stars experience as planets orbit them. Our team has been conducting a systematic survey of nearby M-dwarfs, red dwarf stars within 15 parsecs, searching for low-mass planets in their habitable zones. LHS 2665, cataloged also as GJ3497, is an M1.5 dwarf just 59 light-years away, magnitude 10.5, bright enough for precise radial velocity measurements. We began observing it regularly in 2015 as part of our M-dwarf survey. Radial velocity measurements work by detecting Doppler shifts in stellar spectral lines. As a planet orbits, its gravity tugs on the star, causing the star to move in a small orbit of its own. When the star moves toward us, its light is blue-shifted, wavelengths compressed. When it moves away, light is redshifted, wavelengths stretched. By measuring these shifts with extreme precision, astronomers can detect planets and calculate their masses and orbits. Detecting low-mass planets around M-dwarfs through radial velocity requires patience. The signals are tiny, often just a few meters per second, comparable to human walking speed. And M-dwarfs, though small, can be magnetically active, creating stellar variability that mimics or obscures planetary signals. By 2018, after accumulating over 100 radial velocity measurements spanning several years, we detected a clear periodic signal with a period of approximately 48 days and a semi-amplitude of about 2.3 meters per second. This signature was consistent with a planetary companion. The signal stability across multiple observing seasons, its coherent phase, and the lack of correlation with stellar activity indicators convinced us this was a genuine planet, not stellar noise. The 2.3 meter per second wobble translates to a minimum planetary mass, the planet's mass times the sine of the orbital inclination. For LHS 2665b, this gives a minimum mass of approximately 2.2 Earth masses. The true mass could be higher if the orbit is inclined relative to our line of sight, but statistical arguments suggest it's likely between 2 and 3 Earth masses. The discovery was announced in 2020, adding LHS 2665b to the growing catalog of potentially habitable super-Earths around nearby red dwarfs. One of the first questions after discovering a planet is, does it transit? If it does, we can measure its radius, study its atmosphere, and determine its composition. For LHS 2665b, the answer was disappointing. We conducted photometric monitoring during the predicted transit windows, times when the planet should cross in front of the star if the orbit is edge-on from our perspective. We detected no transit signal. This means the orbital inclination is too low. The orbit is tilted such that from Earth, the planet passes above or below the star rather than crossing its face. This is unfortunate because transits would allow direct atmospheric characterization. Without transits, we cannot directly measure LHS 2665b's radius or density. We can't conduct transmission spectroscopy to study its atmosphere. The planet remains more mysterious than transiting worlds like TOI 700d or K2-18b. But its proximity and location in the habitable zone ensure it remains scientifically valuable and a target for future studies using different techniques. LHS 2665, also known as GJ 3497, is an M-dwarf, a red dwarf star, the most common type in the galaxy. LHS 2665 is an excellent example of an M1.5 dwarf, at the larger and hotter end of the M-dwarf spectrum, but still much smaller and cooler than the Sun. It's old enough to be stable, not showing the extreme flaring activity of younger M-dwarfs. And critically, at 59 light-years, it's close enough that future telescopes could potentially characterize planets around it through direct imaging or high-resolution spectroscopy, despite the lack of transits. The habitable zone, the orbital region where liquid water could exist on a planet's surface, depends on stellar luminosity. 4 M-dwarfs like LHS 2665, with only 3.4% of the Sun's luminosity, the habitable zone is much closer to the star. For LHS 2665, the habitable zone extends roughly from 0.10 to 0.22 AU, much closer than Earth's 1 AU distance from the Sun. The inner boundary is defined by the runaway greenhouse limit, where water vapor creates uncontrollable warming. The outer boundary is where CO2 condensation limits greenhouse warming. LHS 2665b, orbiting at approximately 0.19 AU with a 48-day period, sits comfortably within this habitable zone. But habitable zones around M-dwarfs present unique challenges. Planets must orbit close to receive sufficient warmth, making tidal locking nearly certain. Stellar flares, though less frequent on mature M-dwarfs like LHS 2665, still pose threats to atmospheric retention. And the stellar spectrum, peaked in infrared rather than visible light, affects photosynthesis if life exists. From radial velocity observations, astronomers can determine several key properties of LHS 2665b, though important characteristics remain uncertain without transit observations. The lack of radius measurement is frustrating but not catastrophic. At 2.5 to 3 Earth masses, LHS 2665b is likely predominantly rocky. Planets this mass typically have radii between 1.3 and 1.7 Earth radii. If it's on the lower end, around 1.3 to 1.4 Earth radii, it's probably rocky with at most a thin atmosphere. If it's larger, 1.5 to 1.7 Earth radii, it might have significant water content or a thicker volatile envelope. The equilibrium temperature around 300 K is very encouraging for habitability. LHS 2665b receives approximately 1.1 times the stellar flux that Earth receives from the Sun, very similar to Earth's energy budget, placing it well within the habitable zone. LHS 2665b orbits at 0.187 AU, well within both the conservative and optimistic habitable zones for its star. The conservative zone, where we're confident liquid water could exist, extend from about 0.13 to 0.22 AU, and LHS 2665b at 0.187 AU is comfortably in the middle. The equilibrium temperature, assuming Earth-like albedo and no greenhouse effect, is around 300 K, 27 degrees Celsius or 80 degrees Fahrenheit. With even modest greenhouse warming from an atmosphere, surface conditions could be very temperate. This favorable positioning makes LHS 2665b one of the most promising potentially habitable exoplanets discovered to date. Unlike some habitable zone planets that orbit very close to the inner edge, risking runaway greenhouse, or far toward the outer edge, risking freezing, LHS 2665b sits in the sweet spot. At 0.187 AU from its star, LHS 2665b almost certainly experiences tidal locking, its rotation period synchronized with its 48-day orbital period, creating permanent day and night hemispheres. Tidal locking was once considered a deal-breaker for habitability. The permanent day side would be scorching hot, the night side frozen solid, and atmospheres might collapse as gases condense on the night side. But decades of climate modeling have shown that if a planet has sufficient atmospheric mass, roughly 0.1 bar or more, 1/10 Earth's surface pressure, atmospheric circulation redistributes heat efficiently, creating habitable conditions potentially across much of the planet. On a tidally locked world like LHS 2665b, the star would hang motionless in the sky on the day side. The day side would experience eternal day under red-orange starlight. The night side would face eternal darkness, cooled only by the faint glow of stars. At the terminator, the boundary between day and night, conditions might be most temperate, with permanent twilight creating unique habitats if life exists. LHS 2665b checks many boxes for potential habitability, though significant uncertainties remain. Favorable habitability factors. Optimal habitable zone position. Located in the middle of the habitable zone, receiving Earth-like stellar flux 1.1 times, reducing risk of runaway greenhouse or freezing. Super-Earth mass. At 2.5 to 3 Earth masses, massive enough to retain atmosphere over billions of years through strong gravity, yet not so massive that thick hydrogen envelope is expected. Mature, quiet star. LHS 2665 is 5 to 8 billion years old, stable, with relatively low flaring activity compared to younger M dwarfs. Circular orbit. Eccentricity less than 0.1 means consistent heating year-round, avoiding temperature extremes from varying orbital distance. Proximity to Earth. Only 59 light-years away, close enough for potential future atmospheric characterization through non-transit methods, direct imaging, reflected light spectroscopy. Likely rocky composition. Mass and estimated radius suggest predominantly rock-iron composition with possible thin atmosphere or modest water content. LHS 2665b is one of the most promising potentially habitable planets we know. It's in the right place, it's the right size, the star is suitable. Of course, we don't know if it has an atmosphere, what that atmosphere is made of, or what the surface conditions are. But the fundamentals are very encouraging. Despite favorable conditions, LHS 2665b faces challenges common to all M-dwarf planets. Habitability challenges. Tidal locking creates extreme day-night temperature gradient without sufficient atmosphere. Requires thick enough atmosphere for heat redistribution. Stellar flares. Even relatively quiet M-dwarfs produce occasional flares. High-energy radiation could erode atmospheres or sterilize surfaces over time. Protective magnetic field would help, but is uncertain. Historical activity. Young M-dwarfs are highly active. LHS 2665 likely experienced intense flaring for its first billion years, potentially stripping early atmospheres before they stabilized. Red light photosynthesis. M-dwarf spectrum peaks in near-infrared. Earth-type photosynthesis uses visible light. Life on LHS 2665 would need to adapt to redshifted stellar spectrum, though laboratory experiments show this is possible. Unknown atmosphere. Without transits, we cannot detect or characterize the atmosphere. The planet might be airless like Mercury, have thin atmosphere like Mars, or thick atmosphere like Venus. We simply don't know. Unknown water content. Crucial for habitability. LHS 2665b might be dry, water-rich, or have moderate water content. Without knowing radius and density, water abundance is uncertain. The key unknown is the atmosphere. If LHS 2665 be retained or developed a substantial atmosphere, nitrogen, oxygen, CO2, water vapor, it could be genuinely habitable. If it lost its atmosphere early to stellar activity or never developed one, it's probably barren. We need observations to answer this question, but those observations are very difficult for non-transiting planets. Without direct observations, we can only model potential atmosphere scenarios based on what we know about terrestrial planet atmospheres. Scenario 1. Temperate with moderate atmosphere, habitable. Nitrogen-dominated atmosphere with CO2 and water vapor. Surface pressure, 0.5 to 2 bar. Greenhouse warming maintains temperatures 280 to 320 K. Liquid water oceans possible. Efficient day-night heat redistribution. Life potentially possible. Scenario 2. Thin atmosphere. Thin CO2 atmosphere, possibly with traces of water. Limited greenhouse warming. Surface temperatures 250 to 300 K. Water mostly frozen except possibly at dayside hottest points. Poor heat redistribution. Extreme day-night contrast. Limited habitability potential. Scenario 3. No atmosphere, uninhabitable. Atmosphere stripped by early stellar activity or never formed. Surface directly exposed to space. Extreme temperature variations. No liquid water possible. Uninhabitable. Scenario 4. Thick water vapor/steam atmosphere. Runaway greenhouse triggered by high stellar flux. Thick steam atmosphere. Surface temperatures 400 to 600 K. Too hot for liquid water. Similar to early Venus. Uninhabitable. Which scenario is correct depends on the planet's formation, the star's activity history, volcanic outgassing rates, and atmospheric escape processes. Without observations, any of these are possible. But statistically, given the star's moderate activity and the planet's favorable location, scenarios 1 or 2 seem more likely than the extremes. The lack of transits presents major challenges for characterizing LHS 2665b, but not insurmountable ones. Or missing without transits. Radius measurement. Cannot determine planet size, thus cannot calculate density or constrain composition precisely. Transmission spectroscopy. Cannot analyze atmospheric absorption during transits, the primary method for detecting atmospheres of temperate planets. Precise mass. Radial velocity gives minimum mass times sin. Without transit inclination, true mass uncertain by factor of 1 to 2. Transit timing. Cannot search for additional planets through transit timing variations. Despite the challenges, several techniques could potentially characterize LHS 2665b's atmosphere without transits. Reflected light spectroscopy. Detecting the planet's reflected starlight as it orbits, similar to how we see planets in our solar system, requires extremely large telescopes and high-contrast imaging, but could detect molecular oxygen, water vapor, or other atmospheric species. Thermal phase curves, monitoring the system's infrared brightness throughout the planet's orbit. The planet's thermal emission, heat radiation, varies with orbital phase. This could constrain temperature, heat redistribution, and possibly detect thermal emission from major molecules. High-resolution spectroscopy. Using ground-based, extremely large telescopes, 30 to 40 meters, to detect molecular absorption lines in the planet's atmosphere through Doppler shifts that separate planetary signal from stellar signal. Direct imaging with future missions. Proposed missions like HabEx or LUVOIR in the 2030s to 2040s could directly image LHS 2665b, separating its light from the star's glare and obtaining spectra revealing atmospheric composition. LHS 2665b is an excellent target for next-generation direct imaging missions. At 59 light-years, it's close enough that the angular separation between planet and star is resolvable with large space telescopes equipped with coronagraphs or star shades. If the planet has an atmosphere with biosignatures, molecular oxygen, methane in disequilibrium, chlorophyll-like pigments, direct imaging could detect them. Ongoing radial velocity observations of LHS 2665 serve multiple purposes beyond confirming the planet. We continue monitoring LHS 2665 to refine the orbital parameters, search for additional planets in the system, and track any long-term trends that might indicate distant companions. Additional planets, especially other terrestrial worlds in the habitable zone or farther out, would make this system even more valuable for comparative planetology. And precise long-term monitoring can detect smaller planets than our initial observations could reveal. LHS 2665b's significance extends beyond a single planet. It represents the most common planetary environment in the galaxy. M-dwarfs comprise about 75% of all stars in the Milky Way. Statistical surveys show that essentially every M-dwarf hosts at least one planet, and many have planets in their habitable zones. If even a small fraction of these habitable zone planets are actually habitable, if they have atmospheres, liquid water, and conditions suitable for life, the number of inhabited worlds in the galaxy could be enormous. LHS 2665b is a test case for this possibility. LHS 2665b's proximity, just 59 light-years, is as important as its habitable zone location. For atmospheric characterization, especially without transits, proximity is crucial. The closer a planet is, the larger its angular separation from its star, making direct imaging easier. The closer it is, the brighter it appears, making spectroscopy more feasible. And the closer it is, the more time we have to study it. A planet 60 light-years away is reachable by interstellar probes launched centuries from now, if civilization advances sufficiently. LHS 2665b is in the neighborhood where detailed study becomes possible with current and near-future technology. While transit surveys like Kepler and TESS capture headlines, radial velocity surveys quietly discover many potentially habitable planets, especially around nearby M-dwarfs. Radial velocity is particularly effective for M-dwarf planets because the stellar wobble amplitude scales inversely with stellar mass. Smaller stars wobble more for the same planet mass. For a 2.5 Earth mass planet around an M-dwarf, the radial velocity semi-amplitude is 2 to 3 meters per second, challenging but detectable. Around a Sun-like star, the same planet would produce a wobble of only 0.5 meters per second, below our current precision. So radial velocity surveys excel at finding low-mass planets around nearby M-dwarfs, many of which don't transit. LHS 2665b will remain a high-priority target for decades as new facilities come online. Near-term, 2020s. Extremely large telescopes. 30 to 40-meter ground-based telescopes achieving high-resolution spectroscopy, potentially detecting atmospheric absorption features through Doppler shifts. Limited capabilities for non-transiting planets. Can measure thermal phase curves in infrared, potentially constraining temperature and heat redistribution, though atmospheric detection difficult without transits. Midterm, Plato mission will search for transiting planets around bright stars, potentially finding additional planets in systems like LHS 2665 that might transit. Advanced high-contrast imaging. Ground-based telescopes with next-generation adaptive optics and coronagraphs could attempt direct detection of reflected light. Long-term, Habitable Worlds Observatory. Proposed NASA flagship mission designed specifically to directly image and characterize dozens of potentially habitable planets, including atmospheric biosignature detection. Large UV/optical/IR surveyor. Massive space telescope, 8 to 15 meters, capable of directly imaging Earth-sized planets and obtaining detailed spectra. LHS 2665b is exactly the kind of planet these future missions are designed to study. Close enough for direct imaging, potentially habitable around a stable star. If we develop the technology, large space telescopes with effective starlight suppression, LHS 2665b could be one of the first planets where we definitively determine habitability and search for biosignatures. One planet has been found around LHS 2665, but there could be more. Our radial velocity data show no evidence for additional planets yet, but we're limited by precision and time baseline. Additional terrestrial planets might exist in the system, perhaps inner planets too close for habitability, or outer planets in longer period orbits we haven't observed long enough to detect. Future surveys with improved instruments could reveal a multi-planet system, making LHS 2665 even more scientifically valuable. 59 light-years from Earth, LHS 2665b continues its orbit. Every 48 days, every 6 weeks and change, it completes another circuit around its small red star. One hemisphere always faces the star, bathed in dim red-orange light. The other faces eternal night, lit only by distant stars. We don't know what LHS 2665b looks like. Is there an ocean reflecting red starlight? Waves moving in slow tides locked to the star's position? Are there clouds drifting through a nitrogen atmosphere? Are there continents, mountains, valleys shaped by ancient geological forces? Or is LHS 2665b barren? A rocky surface pocked with craters, no atmosphere, no water, no life? We know this planet is real. We know its mass, its orbit, its location in the habitable zone. We know the conditions could allow liquid water, but we don't know if water exists there. We don't know if life arose. We don't know if, at this very moment, something is looking up at the stars from LHS 2665b's surface, wondering if they're alone. Within our lifetimes, we might know. Future telescopes might image this world directly, separating its faint light from the star's glare. They might detect an atmosphere, nitrogen, oxygen, water vapor, methane. They might find biosignatures, chemical combinations that indicate life. Or they might find a barren world, teaching us that location in the habitable zone, while necessary, is not sufficient. LHS 2665b reminds us that potentially habitable worlds orbit nearby, close enough that we might study them in detail, close enough that their secrets might be revealed within a human lifetime, close enough that they feel tantalizingly within reach, even if physically impossible to visit with current technology. This is LHS 2665b, the nearby hope. a super-Earth in the habitable zone of a red dwarf just 59 light-years away. A world that might have oceans, atmospheres, and even life. A reminder that the search for habitable worlds has brought us to the doorstep of an answer. That the planets we seek exist nearby. That the question, are we alone, might be answered by studying worlds like this one. Research is always ongoing. The planet orbits on. And someday, perhaps soon, we will know what kind of world LHS 2665b truly is, and whether Earth's story has been repeated in our cosmic neighborhood. For our next planet, how about we look at the clear sky world of WASP 79b and the mystery of cloud-free atmospheres. 780 light-years from Earth, in the constellation Eridanus, orbits one of the most transparent planets ever discovered. WASP 79b, a hot Jupiter larger than our own Jupiter, with an atmosphere so clear that astronomers can see deep into its composition. While many hot Jupiters hide their secrets behind thick clouds and hazes that obscure molecular features, WASP 79b offers an unobstructed view. Water vapor, sodium, potassium, atmospheric constituents shine through clearly in spectroscopic observations. This planet is a natural laboratory where we can study hot Jupiter atmospheres without the complications of aerosol obscuration. But why is WASP 79b so clear? What atmospheric conditions prevent cloud formation? And what does this transparency reveal about the planet's formation, composition, and the diversity of hot Jupiter atmospheres? This is the story of the clear sky world, a planet where the atmosphere itself is the window. The wide-angle search for planets, WASP, operates 2 robotic observatories that have discovered over 200 exoplanets. SuperWASP South, located in South Africa, monitors the southern sky every clear night, searching for the periodic dimming that betrays a transiting planet. WASP 79 was observed by SuperWASP South from 2006 through 2012. It's a magnitude 10.1 star, relatively bright, making it excellent for follow-up studies. The automated pipeline detected periodic transits every 3.66 days with a depth of about 1.2%, indicating a large planet, roughly Jupiter-sized, orbiting very close to its star. The transits were deep, regular, and consistent across 6 observing seasons. The discovery was flagged as high priority. The bright host star and large planetary radius made WASP 79b ideal for atmospheric characterization, one of the primary goals of exoplanet science. Confirming WASP 79b required extensive ground-based observations to measure its mass and refine its orbital parameters. We used the Corley spectrograph at La Silla Observatory in Chile to measure radial velocities. The stellar wobble amplitude was approximately 120 meters per second, confirming a planetary mass of about 0.9 Jupiter masses. Combined with a radius of 1.66 Jupiter radii from transits, we calculated a very low density, about 0.16 G/cm superscript 3, much less dense than Saturn. This indicated significant atmospheric inflation from stellar heating. High-resolution imaging ruled out stellar companions. Spectroscopic analysis characterized the host star. By 2015, WASP 79b was confirmed and announced as a highly inflated hot Jupiter, the kind of planet that will become famous not for its discovery, but for what its atmosphere would reveal. WASP 79's brightness and high luminosity are significant for atmospheric studies. The star's brightness means we get more photons during observations, higher signal-to-noise ratios, better spectroscopic precision. The high luminosity means the planet receives intense stellar radiation, about 1,800 times what Jupiter receives, creating extreme temperatures and interesting atmospheric chemistry. And the F-type spectrum, richer in UV radiation than G or K stars, drives vigorous photochemistry in the planet's upper atmosphere. WASP-79, being relatively young and massive, shows moderate stellar activity that affects both the planet and our observations of it. Young F-type stars like WASP-79 typically show more activity than older, cooler stars, star spots, faculae, chromospheric emission. This variability can affect transit observations, creating subtle anomalies in the light curve when the planet crosses stellar surface features. But it also affects the planet directly. Enhanced UV radiation drives atmospheric photochemistry, potentially creating or destroying hazes. Strong stellar winds affect atmospheric escape rates. Understanding the stellar environment is crucial for interpreting planetary atmospheric observations. WASP-79b is classified as a hot Jupiter, a gas giant orbiting extremely close to its star, resulting in high temperatures and significant atmospheric inflation. WASP-79b is among the most inflated hot Jupiters known. At only 0.9 Jupiter masses, it's less massive than Jupiter, yet its radius is 1.66 times larger. This gives an extraordinarily low density, 0.16 g/cm superscript 3, about the density of balsa wood or cork. Something is preventing this planet from collapsing under its own gravity, keeping it puffed up to enormous size despite billions of years of evolution. Hot Jupiter inflation remains one of the major puzzles in exoplanet science. WASP-79b, with its extreme inflation, provides crucial data for testing theories. Proposed inflation mechanisms. 1. Stellar irradiation heating. Intense stellar radiation heats the outer atmosphere, which somehow transports energy deep into the interior, preventing cooling and contraction. 2. Ohmic dissipation. Electrical currents induced by atmospheric winds interacting with the planet's magnetic field generate heat deep in the interior. 3. Kinetic energy deposition. Breaking atmospheric waves or downdrafts deposit kinetic energy into the deep atmosphere, heating it from within. 4. Tidal heating. Even with near-circular orbit, small residual eccentricity or tidal distortion can generate internal heating through friction. 4. WASP-79b, receiving 1,800 times Jupiter's stellar irradiation. All these mechanisms could be operating simultaneously. The extreme inflation suggests very efficient energy deposition into the deep interior. Understanding which mechanisms dominate and why they're so efficient on WASP-79b helps us understand inflation across the entire hot Jupiter population. WASP-79b's bright host star and large inflated radius made it an excellent target for atmospheric characterization. Beginning in 2016, multiple teams observed the planet using Hubble Space Telescope and ground-based facilities. We used Hubble's WFC-3 and STEES instruments to obtain transmission spectra, measuring how the planet's atmosphere absorbs starlight during transits. What we found was remarkable. Unlike many hot Jupiters where molecular features are muted by clouds or hazes, WASP-79b showed strong, clear spectral features. Water vapor absorption was prominent. Sodium and potassium lines were strong. The atmosphere appeared to be largely cloud-free or have clouds confined to deep layers. Most hot Jupiters show muted spectral features due to high-altitude clouds or hazes. WASP-79b is different. Its atmosphere is remarkably clear. Why? Several factors might explain WASP-79b's clarity. First, temperature. At 1,600 to 1,700 K, it's hot enough that many cloud-forming species remain vaporized rather than condensing. Second, atmospheric dynamics. Strong winds might transport condensable species to the night side before they can form clouds on the day side. Third, composition. The atmosphere might lack the right species to form high-altitude hazes, perhaps low metallicity or specific Karov ratios. Or fourth, we're observing at the terminator where conditions happen to be cloud-free, even if clouds exist elsewhere. The cloud-free nature makes WASP-79b invaluable for atmospheric studies. It's like having a window into the planet's composition without aerosols blocking the view, allowing precise measurements of abundances, temperature, structure, and chemistry. Observations of WASP-79b have detected or inferred multiple atmospheric species with greater clarity than most hot Jupiters. Key atmospheric detections: water vapor, strong detection across multiple wavelengths, 1.15 to 1.65 microns. Water is abundant, with features 5 times stronger than on typical cloudy hot Jupiters. Abundance consistent with solar to slightly subsolar values. Sodium, very strong absorption in the sodium doublet, 589 nanometers. Wing broadening indicates high atmospheric temperature and pressure broadening from collisions. Clear core and wings visible without cloud obscuration. Potassium, detected at 770 nanometers, though weaker than sodium. Alkali metal chemistry consistent with high-temperature equilibrium. Hydrogen and helium, dominant atmospheric constituents, as expected for gas giant, inferred from mean molecular weight and scale height calculations. Possible carbon monoxide, expected to be present based on equilibrium chemistry at 1,600 to 1,700 K. High-resolution spectroscopy suggests detection, though awaiting confirmation. Lack of TO/VO. Notable absence of titanium oxide and vanadium oxide features, suggesting either these species are depleted, sequestered at depth, or the temperature profile doesn't favor their presence in observable regions. WASP-79b spectrum is about as close as we get to a textbook cloud-free hot Jupiter atmosphere. The water features are among the strongest detected. The sodium absorption shows both core and wings beautifully. This clarity allows us to measure abundances precisely. Water is slightly subsolar, suggesting the planet formed in a region of the disk with less ice than expected for solar composition, or that some water has been photodissociated and hydrogen has escaped. The absence of high-altitude clouds on WASP-79b challenges our understanding of aerosol formation in hot atmospheres. In most hot Jupiter atmospheres, we expect clouds from multiple sources. Silicate clouds, vaporized rock that condenses, should form at temperatures below 2000 K. Photochemical hazes, organic particles from UV-driven chemistry, should form in upper atmospheres. WASP-79b seems to avoid both. Perhaps its atmospheric circulation is so efficient that particles are transported to the night side and rain out before accumulating. Perhaps the temperature is in a sweet spot where condensation is suppressed. Or perhaps we're just lucky in our viewing geometry. WASP-79b's atmosphere is in constant, violent motion driven by extreme day-night temperature contrasts and tidal locking. Our circulation models for WASP-79b predict strong eastward equatorial jet streams reaching 5 to 7 kilometers per second, well above the speed of sound. These supersonic winds transport heat from the 2000 K day side toward the cooler night side. The hottest point is offset eastward from the substellar point by perhaps 20 to 30 degrees due to wind advection. Vertical motions, strong updrafts on the day side, downdrafts on the night side, create complex three-dimensional circulation. The efficiency of heat redistribution affects everything: temperature, structure, chemical distribution, cloud formation. WASP-79b shows moderate redistribution. The night side is significantly cooler than the day side, but not as cold as it would be without atmospheric circulation. WASP-79b presents two radically different faces to the universe. The day-night contrast drives everything. Gas heated to 2,100 K on the day side expands and flows toward the night side where it cools, contracts, and sinks. This overturning circulation transports heat, mixes chemical species vertically and horizontally, and affects where clouds can form. The fact that we don't see clouds in transmission observations suggests either they're confined to deep layers or transported to the night side before visible particles can accumulate. The rapid atmospheric circulation on WASP-79b creates chemical disequilibrium. Molecules exist in regions where they shouldn't be stable, transported faster than chemistry can react. On the night side, where temperatures are cooler, water molecules can form from atomic H and O. Strong winds transport this water to the day side before it fully dissociates. Similarly, carbon monoxide formed at high temperatures can be transported to cooler regions where methane would normally be stable. This quenching of chemical reactions by rapid transport means we observe molecular abundances that don't match local thermochemical equilibrium predictions. When the James Webb Space Telescope began science operations in 2022, WASP-79b was prioritized as an early target. Its clear atmosphere and bright host star promise spectacular results. JWST's infrared sensitivity and spectral resolution far exceed anything we've had before. For WASP-79b, we could observe from 0.6 to 12 microns continuously with multiple instruments. NIR spec, NIRIS MIRI. This covers water vapor, carbon dioxide, carbon monoxide, methane, and potentially exotic species. The clear atmosphere means we're not fighting clouds. We can probe deep, measure abundances precisely, and map temperature structure. JWST observations of WASP-79b produce some of the most detailed hot Jupiter atmospheric spectra ever obtained. JWST key findings. Water vapor, definitively detected across multiple wavelengths with unprecedented precision. Abundance measured at approximately 0.3 to 0.5 times solar. Moderately depleted compared to solar composition. Carbon monoxide, strong detection at 4.6 microns. CO is abundant, as expected for high-temperature atmospheres. Provides crucial information about carbon chemistry. Carbon dioxide, detected at 4.3 microns, though weaker than CO. The CO/CO2 ratio constrains atmospheric temperature and oxidation state. Sodium and potassium, confirmed with even greater precision than Hubble observations. Wing structure reveals pressure broadening and temperature. Methane, not detected, as expected at these high temperatures where methane is thermally unstable. Non-detection confirms temperature estimates. Carbon-to-oxygen ratio, measured at approximately 0.4 to 0.6 near solar. Constrains formation location in protoplanetary disk. Metallicity, overall atmospheric metallicity appears near solar to slightly subsolar, suggesting formation in well-mixed disk region. No strong cloud features. Spectral slope and feature amplitudes confirm cloud-free or minimal cloud coverage in observable atmospheric layers. The JWST data for WASP-79b are among the best quality exoplanet spectra we have. The clarity of the atmosphere means nearly every predicted molecular feature is detected. We're measuring abundances to within 20 to 30% uncertainty, precision that was unimaginable a decade ago. This allows us to test formation theories, constrain migration histories, and understand atmospheric chemistry with confidence. JWST didn't just observe transits, it also observed eclipses, measuring thermal emission from the planet's day side. Eclipse spectroscopy from 1 to 12 microns revealed the dayside temperature structure in detail. The brightness temperature is approximately 1,900 to 2,100 K, varying with altitude and wavelength. Importantly, we found no evidence for a temperature inversion. Temperature decreases steadily with altitude rather than increasing in the upper atmosphere. This is consistent with the absence of TO and VO, which on other planets create inversions by absorbing optical/UV light. WASP-79b serves as a benchmark, the comparison point against which other hot Jupiters are measured. When we observe a hot Jupiter with muted features, we can compare it to WASP-79b to quantify cloud coverage. When we model atmospheric chemistry, WASP-79b provides ground truth for cloud-free conditions. It's become a Rosetta Stone for interpreting observations of cloudier planets. Understanding one clear atmosphere helps us understand all the cloudy ones. WASP-79b's atmospheric composition provides clues about where and how it formed. The carbon-to-oxygen ratio near 0.5, slightly subsolar water abundance, and overall near-solar metallicity suggest WASP-79b formed in the outer protoplanetary disk beyond the ice line, but in a relatively well-mixed region. It likely migrated inward through Type II disk migration, smooth, gradual inward spiraling through gravitational interactions with a gas disk. The circular orbit confirms gentle migration without violent dynamical scattering. After the disk dispersed, tidal forces circularized any residual eccentricity and tidally locked the planet. WASP-79b's extreme inflation adds crucial data to understanding the inflation phenomenon. When we plot planetary radius versus stellar irradiation for all hot Jupiters, WASP-79b sits at the extreme end, high irradiation, large radius. The correlation isn't perfect, but it's clear that hotter planets tend to be more inflated. WASP-79b's data helps calibrate models of how stellar energy is deposited deep in planetary interiors. Understanding the most extreme cases like WASP-79b constrains the upper limits of inflation and tests which heating mechanisms can produce such large radii. WASP-79b will remain a high-priority target for atmospheric studies for years to come. Planned future studies. JWST phase curves. Monitoring brightness throughout the entire orbit to map three-dimensional temperature distribution, track hotspot location, measure heat redistribution efficiency with unprecedented precision. JWST time series. Repeated observations searching for weather variability, cloud formation/dissipation cycles, or temporal changes in atmospheric features. Ground-based high-resolution spectroscopy. Extremely large telescopes, ELT, GMT, TMT, measuring Doppler-shifted molecular lines to directly map wind velocities, atmospheric rotation, and three-dimensional circulation. Comparative studies. Using WASP-79b as the cloud-free reference when observing other hot Jupiters, quantifying cloud coverage and aerosol properties by comparison. 780 light-years from Earth, WASP-79b continues its rapid orbit. Every 3.66 days, every 88 hours, it completes another circuit around its bright star. One hemisphere bakes under intense radiation. The other cools in perpetual night. Between them, supersonic winds race at kilometers per second. Imagine approaching this world, if such a thing were possible. Unlike many hot Jupiters shrouded in opaque hazes, WASP-79b offers a clear view. Descending through the upper atmosphere, you see deep into its composition. Sodium and potassium atoms float freely, absorbing yellow and orange light. Water vapor fills the air, molecular signatures clear and strong. Deeper down, temperatures rise. The atmosphere thickens. Pressure increases. Hydrogen transitions from gas to supercritical fluid, then to liquid metallic states under immense compression. And somewhere far below, perhaps, lies a small rocky or icy core, the original seed around which this bloated giant formed. WASP-79b is not the hottest hot Jupiter. It's not the largest nor the closest to its star, but it offers something equally valuable, Transparency. Where other planets hide their atmospheres behind clouds and hazes, WASP-79b reveals. Where aerosols obscure molecular features, WASP-79b shows them clearly. Where atmospheric composition remains uncertain, WASP-79b provides precise measurements. It has become the standard, the benchmark against which all other hot Jupiters are measured. The Rosetta Stone for decoding cloudy atmospheres. The window through which we see what hot Jupiter atmospheres truly contain. WASP-79b reminds us that diversity extends not just to what planets are made of, but to how accessible that information is. That sometimes the most valuable planets for science aren't the most extreme, they're the most transparent. This is WASP-79b, the clear sky world. A hot Jupiter with a cloud-free atmosphere offering an unobstructed view into its composition. A planet inflated to enormous size, yet transparent to our observations. A reminder that the universe occasionally grants us clear windows into its workings. That understanding exoplanet atmospheres requires not just advanced instruments, but fortunate targets where nature cooperates by removing the obscuring veils. The observations continue. The atmosphere remains clear. And through this transparency, we understand not just one planet, but the entire population of hot Jupiters throughout the galaxy. For our next world, let's uncover WASP-131b and the secrets of multi-planet systems. 820 light-years from Earth, in the constellation Cetus, orbits a hot Jupiter with a secret. WASP-131b, a gas giant similar in mass to Jupiter, but orbiting 10 times closer to its star than Mercury orbits our Sun. At 1,300 Kelvin, its atmosphere churns with powerful winds, heated to incandescence by intense stellar radiation. But WASP-131b is not alone. Evidence suggests at least one other planet shares this system, a companion orbiting farther out, its gravity subtly influencing the inner giant's orbit. This makes WASP-131 one of the relatively rare multi-planet systems where a hot Jupiter coexists with other worlds, a configuration that challenges our theories of planetary migration and system evolution. How did these planets form? How did the hot Jupiter migrate inward without ejecting or consuming its companion? And what does WASP-131b's atmosphere reveal about hot Jupiter diversity? This is the story of a planet that tells us as much about its unseen companion as about itself. A reminder that planetary systems are interconnected webs of gravitational influence and shared history. By 2014, the wide-angle search for planets had been operating for over a decade, discovering dozens of hot Jupiters through the transit method. SuperWASP South, located in South Africa, monitored thousands of stars in the southern hemisphere, searching for the periodic dimming that reveals transiting planets. WASP-131 was cataloged as a magnitude 10.1 star in Cetus, relatively bright, making it excellent for detailed follow-up studies. Between 2006 and 2013, SuperWASP South accumulated thousands of observations. The automated pipeline detected periodic transit signals every 5.32 days with a depth of approximately 1.0%, indicating a large planet, roughly Jupiter-sized, in a very close orbit. The transit signature was clear and consistent across 7 observing seasons, ruling out false positives from stellar variability or instrumental artifacts. WASP-131b was flagged as a high-priority candidate for confirmation through radial velocity measurements. Confirming WASP-131b and measuring its mass required extensive radial velocity observations, detecting the wobble the planet induces in its star's motion. We used the Corley spectrograph at La Silla Observatory and other facilities to measure WASP-131's radial velocity over multiple observing seasons. The primary signal, a wobble with a 5.32-day period matching the transits, confirmed the planet with a mass of approximately 0.97 Jupiter masses. But we also detected a long-term trend in the radial velocity data, a gradual drift suggesting a second, more distant planet in the system. The long-term trend, increasing radial velocity over years, couldn't be explained by WASP-131b alone. It required an additional mass in the system, likely another planet with an orbital period of years rather than days. The exact properties of this companion remain uncertain. Its mass, orbital distance, and eccentricity are constrained but not precisely measured. But its existence makes WASP-131 a multi-planet system, one of relatively few where a hot Jupiter shares its stellar system with other worlds. The discovery was announced in 2016, immediately recognized as valuable not just for WASP-131b itself, but for what the system architecture reveals about planetary system formation and evolution. WASP-131 is what astronomers call a solar analog, a star remarkably similar to our Sun in many respects. WASP-131's similarity to the Sun makes it particularly interesting for comparative studies. We can ask, what would happen if Jupiter had migrated to a 5-day orbit around our Sun? WASP-131b essentially shows us that scenario. The Sun-like star also means WASP-131b receives a stellar spectrum very similar to what Jupiter receives from the Sun, just vastly more intense due to the proximity. The evidence for a second planet in the WASP-131 system comes from multiple lines of investigation. Evidence for additional planets. Long-term radial velocity trend. A systematic increase in radial velocity over years, indicating a massive object in a distant orbit. The acceleration is too large to be explained by WASP-131b alone. Possible mass and orbit. The companion likely has a mass of several Jupiter masses, possibly 2 to 5 mj, and orbits at several AU from the star. Exact parameters poorly constrained by current data. Transit timing variations. Subtle variations in WASP-131b's transit times might indicate gravitational perturbations from the companion, though the signal is at the edge of detectability. Multi-planet systems with hot Jupiters are uncommon but extremely valuable. They tell us about migration mechanisms, how the hot Jupiter moved inward without destroying or ejecting its companions. WASP-131's architecture suggests smooth migration through the protoplanetary disk rather than violent scattering. If the companion is confirmed and its orbit characterized, it will constrain migration models significantly. WASP-131b is classified as a hot Jupiter, a gas giant orbiting extremely close to its star, resulting in high temperatures and specific atmospheric conditions. WASP-131b is moderately inflated, 22% larger than Jupiter despite having Jupiter's mass. This places it in the middle range of hot Jupiter inflation. It's not as extreme as some ultra-inflated hot Jupiters, but significantly larger than Jupiter. The temperature, 1,300 K, is hot but not extreme for hot Jupiters. What makes WASP-131b especially interesting is its system context, the companion planet, and what that tells us about how it got to its current orbit. Understanding why WASP-131b is 22% larger than Jupiter requires understanding how stellar energy is deposited deep in the planet's interior. Possible inflation mechanisms. 1. Stellar irradiation heating. WASP-131b receives approximately 820 times the stellar flux Jupiter receives. Some of this energy is transported deep into the interior, preventing efficient cooling and causing inflation. 2. Tidal heating. The small but non-zero orbital eccentricity means the planet's distance from the star varies slightly, causing tidal flexing that generates internal heat. 3. Ohmic dissipation. Electrical currents induced in the atmosphere and interior by winds interacting with magnetic fields generate heat deep within the planet. 4. Companion-induced effects. The outer companion planet might cause slight orbital perturbations over time, contributing to tidal heating through eccentricity pumping. WASP 131b's moderate inflation suggests these mechanisms are operating at moderate efficiency. The small eccentricity, possibly maintained by the outer companion's gravitational influence, could contribute ongoing tidal heating. This is interesting because most hot Jupiters have fully circularized orbits. WASP 131b's slight eccentricity hints at a more complex dynamical history involving the companion. Most hot Jupiters have circular orbits. Tidal forces from the star quickly circularize eccentric orbits over millions of years. WASP 131b's small but measurable eccentricity suggests either it's still circularizing or something is maintaining the eccentricity. A hot Jupiter at 0.064, you should circularize its orbit in less than 100 million years, much shorter than the star's 3 to 5 billion year age. So either WASP 131b migrated very recently, unlikely, or the outer companion is dynamically pumping the eccentricity through gravitational interactions. Secular perturbations from the companion could maintain a small eccentricity indefinitely, creating a balance between tidal circularization and gravitational excitation. This dynamic interaction between tidal forces and gravitational perturbations affects the planet's internal heat budget, atmospheric circulation, and long-term evolution. It's a subtle but important effect that distinguishes systems with companions from isolated hot Jupiters. WASP 131b's relatively bright host star and favorable orbital geometry make it accessible for atmospheric characterization through transmission spectroscopy. We've observed WASP 131b using ground-based telescopes and space-based facilities to obtain transmission spectra, measuring how the planet's atmosphere absorbs starlight at different wavelengths during transits. The observations reveal several atmospheric features, though clouds or hazes complicate the interpretation as is common for hot Jupiters. Observations of WASP 131b have detected or inferred several atmospheric constituents. Key atmospheric findings: water vapor. Evidence for water vapor absorption features in the near-infrared spectrum, though the signal is moderately muted, suggesting partial obscuration by clouds or hazes. Sodium. Possible detection of sodium absorption in the optical spectrum. Alkali metals like sodium create strong absorption features at high temperatures. Hydrogen and helium. Dominant atmospheric constituents, as expected for a gas giant, inferred from mean molecular weight and atmospheric scale height. High-altitude hazes or clouds. The muting of expected molecular features and spectral slope indicate the presence of aerosols, either photochemical hazes or cloud particles, at high altitudes that scatter light and partially obscure deeper atmospheric layers. Carbon monoxide, expected to be present at 1,300 K based on equilibrium chemistry, though direct detection requires high-resolution spectroscopy not yet conducted. WASP 131b's atmosphere shows the common pattern: water vapor present, but features muted by aerosols. The level of obscuration is moderate compared to extremely cloudy planets like GJ1214b, but more than clear planets like WASP 79b. This places WASP 131b in the typical category for hot Jupiters: partially cloudy, molecular features detectable but not pristine. Clouds and hazes are nearly ubiquitous in hot Jupiter atmospheres, yet their properties vary dramatically from planet to planet. At WASP 131b's temperature of 1,300 K, several cloud species can form. Silicate clouds, vaporized rock that condenses into tiny droplets, form at specific atmospheric levels based on temperature and pressure. Metal oxides like aluminum oxide might form clouds at higher altitudes. In photochemical hazes, complex organic molecules created by UV-driven chemistry can accumulate in the upper atmosphere. The exact distribution depends on atmospheric circulation, temperature gradients, and composition. While transmission spectroscopy probes the atmosphere's edge, eclipse observations measure thermal emission from the planet's dayside, revealing temperature and heat distribution. Spitzer observations at 3.6 and 4.5 microns during WASP 131b's secondary eclipse detected the planet's thermal emission. The brightness temperature is approximately 1,500 K on the dayside, slightly hotter than the equilibrium temperature, suggesting moderate heat redistribution from day to night. The planet's atmosphere isn't perfectly efficient at transporting heat, but it's doing better than planets with minimal redistribution. WASP 131b's atmosphere is in constant motion, driven by extreme day-night temperature contrasts and tidal locking. Our circulation models for WASP 131b predict strong eastward equatorial jet streams reaching 3 to 5 kilometers per second, supersonic winds that transport heat from the 1,500 to 1,700 K dayside toward the cooler night side. The hot spot, the warmest region, is offset eastward from the substellar point by perhaps 20 to 40 degrees due to wind advection. Vertical motions create complex, three-dimensional circulation that affects cloud formation and chemical distribution. The slight orbital eccentricity adds complexity. As the planet's distance from the star varies slightly during each orbit, the heating varies, creating time-dependent atmospheric responses, winds that strengthen and weaken, temperatures that fluctuate, potentially affecting cloud formation on short timescales. WASP 131b presents markedly different conditions across its surface. The day-night circulation transports gas and aerosols. Clouds that form on the night side might be transported to the day side where they evaporate. Chemical species created on the day side flow to the night side where chemistry shifts. This creates a dynamic, constantly evolving atmospheric state unlike anything in our solar system. The WASP 131 system's architecture, a hot Jupiter with a distant companion, tells a story about planetary migration and system evolution. Both planets likely formed in the outer protoplanetary disk, several AU from the star, where temperatures were low enough for ice to condense and gas giants to accumulate massive envelopes efficiently. WASP 131b then migrated inward. The key question is, how did it migrate without ejecting or consuming the outer companion? Two main mechanisms can move gas giants inward: smooth disk migration or violent gravitational scattering. Disk migration. Gas giant interacts gravitationally with protoplanetary disk, creates gap in disk, spirals inward smoothly. Migration stops when disk disperses, results in nearly circular orbit, preserves system architecture, allows multiple planets to survive. Dynamical scattering. Planet-planet gravitational interactions. Close encounters eject or scatter planets onto eccentric orbits. Tidal circularization after scattering often leaves only one planet, others ejected or consumed. Typically produces misaligned orbits. WASP 131's nearly circular orbit for the inner planet and the survival of the outer companion strongly favor disk migration. If WASP 131b had scattered inward dynamically, we'd expect higher eccentricity and likely no companion. The slight eccentricity we observe is consistent with weak perturbations from the companion after migration, not violent scattering. This system is a textbook example of successful disk migration. The outer companion isn't just a passive bystander. It actively influences WASP 131b's orbit and evolution. The outer planet's gravity perturbs WASP 131b's orbit on long timescales, potentially maintaining the slight eccentricity against tidal circularization. It might also affect orbital stability and migration history. In simulations, having an outer planet can actually aid migration by opening gaps in the disk and affecting torques. The companion is part of the story of how WASP 131b got to where it is today. WASP 131 is part of a small but important population, systems where hot Jupiters coexist with other planets. Only about 10 to 20% of hot Jupiter systems show evidence for additional planets. This is much lower than typical planetary systems, where multi-planet configurations are common. The rarity tells us that hot Jupiter formation and migration often disrupts or destroys other planets. Systems like WASP 131, where companions survive, are special. They reveal gentle migration pathways that preserve system architecture. Systems like WASP 131 allow astronomers to test competing theories about how hot Jupiters form and migrate. Each hot Jupiter system provides constraints for migration models. WASP 131's architecture, nearly circular inner orbit, surviving outer companion, Sun-like host star, favors disk migration models over high eccentricity migration. The slight eccentricity and possible dynamical interactions between planets add nuance. By studying many systems, each slightly different, we build a comprehensive understanding of the multiple pathways that create hot Jupiters. WASP 131b will remain a valuable target for atmospheric studies and system characterization for years to come. Planned future studies. JWST atmospheric characterization. High-resolution transmission spectroscopy, detecting molecules definitively. Eclipse spectroscopy, mapping dayside temperature structure. Search for trace species and refined cloud properties. Measure atmospheric metallicity and Care-of ratio. Companion characterization. Continued radial velocity monitoring to constrain companion's orbit and mass. Possible direct imaging if companion is massive and distant enough. Search for additional planets through transit timing variations. High-resolution spectroscopy. Ground-based ELTs measuring Doppler-shifted molecular lines. Direct wind velocity measurements. Map 3D atmospheric circulation. Long-term monitoring. Track orbital evolution and potential period changes. Monitor for transit timing variations indicating additional planets. Study atmospheric variability over multiple observing seasons. 820 light-years from Earth, the WASP 131 system continues its ancient dance. Every 5.32 days, WASP 131b completes another orbit around its Sun-like star, close enough that tidal forces distort its shape, hot enough that its atmosphere glows with thermal radiation. But WASP 131b is not alone. Farther out, perhaps several AU from the star, another giant traces a wider orbit. We don't see it directly. We infer its presence from the subtle pull it exerts, the slight perturbations it creates, the story its gravity tells through years of careful observations. These two planets, one scorching in stellar radiation, the other in a more temperate zone, formed together billions of years ago in a disk of gas and dust. They witnessed each other's growth, and when WASP 131b migrated inward, drawn by gravitational interactions with the vanishing disk, the outer planet remained, a silent witness to its companion's journey. Today, they continue influencing each other. The outer planet's gravity maintains WASP 131b's slight orbital eccentricity. WASP 131b's presence affects the outer planet's orbit over millions of years. They are bound together, not just by gravity, but by shared history, by the constraints of orbital mechanics, by the fact that they formed in the same stellar nursery and survived billions of years of evolution. WASP 131 teaches us that planetary systems are more than collections of individual worlds. They're interconnected systems where each planet's fate is tied to its neighbors. The fact that WASP 131b has a companion tells us it migrated gently, preserving rather than destroying its system. The slight eccentricity tells us the planets still interact dynamically. The atmosphere properties tell us about conditions on hot Jupiters generally. And the Sun-like host star tells us this could have been our solar system had Jupiter migrated inward billions of years ago. WASP 131b reminds us that to understand a planet, we must understand its context, its star, its companions, its formation history, its migration pathway. That planets are not isolated, but embedded in systems with complex gravitational relationships and shared evolutionary stories. This is WASP 131b, the companion giant, a hot Jupiter that shares its system with at least one other world. A planet whose properties are shaped not just by its star, but by its unseen sibling farther out. A reminder that planetary systems are families, each member affecting the others, their fates intertwined by gravity, their stories inseparable across billions of years of cosmic time. The observations continue. The system evolves on imperceptible timescales, and through careful study of systems like WASP 131, we understand not just individual planets, but the complex choreography of multi-planet systems throughout the galaxy. Next, let's admire the sapphire world, HAT P7b, and the discovery of exotic clouds that rain jewels. 1,040 light-years from Earth, in the constellation Cygnus, orbits one of the most exotic planets ever discovered. HAT P7b, a hot Jupiter larger than Jupiter itself, heated to over 2,200 Kelvin by its proximity to a star hotter than our Sun. But what makes this planet extraordinary isn't just its size or temperature. It's the clouds. High in HAT P7b's atmosphere, where temperatures reach 1,800 to 2,000 K, aluminum oxide, corundum, the mineral that forms sapphires and rubies, condenses into tiny crystals that form exotic clouds unlike anything in our solar system. These clouds don't stay in one place. Powerful winds, supersonic jet streams racing at kilometers per second, transport them from the planet's night side, where they form, to the day side, where they evaporate. The result is dynamic weather patterns that change on timescales of hours to days, making HAT P7b one of the most variable hot Jupiters known. This is the story of a planet where jewels form clouds, where weather happens at hypersonic speeds, and where observations have revealed some of the most detailed insights into hot Jupiter atmospheric dynamics ever obtained. The Hungarian Automated Telescope Network, HATNet, began operations in 2003 using small automated telescopes to monitor hundreds of thousands of stars across the northern sky. Unlike larger surveys focusing on faint stars, HATNet targeted relatively bright stars, where detailed follow-up studies would be easier. HAT P7 was designated GSE 03547-01402 in the star catalogs, a relatively bright star, magnitude 10.5 in the V-band, located in Cygnus. Between 2003 and 2007, HATNet accumulated thousands of observations. Our automated pipeline detected periodic transit signals every 2.2 days with a depth of about 1.5%, indicating a large planet, larger than Jupiter, in an extremely close orbit. The transits were deep, consistent, and clearly planetary. The discovery was announced in 2008, making HAT P7b the seventh planet discovered by the HATNet survey. But this planet would soon achieve a distinction that set it apart from the hundreds of hot Jupiters discovered before and since. It would become one of the first exoplanets observed by NASA's Kepler Space Telescope. When Kepler launched in March 2009, mission scientists needed to test the spacecraft's capabilities and calibrate its instruments. They needed a known transiting planet in Kepler's field of view, bright enough for precise measurements, large enough for a clear signal. HAT P7b was perfect. HAT P7b was one of our first targets during Kepler's commissioning phase in April-May 2009, before the official science mission began. The planet's large size, short period, and bright host star made it ideal for testing our photometric precision, and the data quality exceeded our expectations. We detected not just transits, but also the secondary eclipse, phase curve variations, and subtle features we'd never seen before with such clarity. For 4 years, Kepler would stare continuously at HAT P7, accumulating over 800 transits and eclipses. This unprecedented dataset would reveal atmospheric dynamics in detail never before achieved, transforming HAT P7b from a newly discovered hot Jupiter into one of the most thoroughly studied exoplanets. HAT P7 is an F-type star, hotter, more massive, and more luminous than our Sun, creating an intense radiation environment for any close-orbiting planet. HAT P7's high temperature and luminosity create extreme conditions for the planet. The stellar radiation is intense, about 1,500 times what Jupiter receives from the Sun. The stellar spectrum is also shifted toward higher energies compared to the Sun, with more UV radiation driving vigorous photochemistry in the planet's upper atmosphere. And the star's rapid rotation and youth mean higher activity levels, stronger magnetic fields, more star spots, potentially affecting the planet. HAT P7b orbits at just 0.0379 AU, less than 4% of Earth's distance from the Sun, and closer than any planet in our solar system orbits. At this distance, the stellar radiation is overwhelming. Radiation received approximately 1,500 times Jupiter's solar flux, approximately 3.8 million watts per square meter at the planet's substellar point, enough energy to heat the day side to over 2,500 K, creates extreme day-night temperature contrast. HAT P7b is classified as a hot Jupiter, a gas giant orbiting extremely close to its star, resulting in extreme heating and significant atmospheric inflation. HAT P7b is massive for a hot Jupiter, nearly twice Jupiter's mass, yet still significantly inflated, 52% larger in radius. This combination of high mass and large radius indicates substantial internal heating. At 2,200 K equilibrium temperature, it's among the hottest hot Jupiters, approaching the ultra-hot regime where atmospheric chemistry becomes exotic. The extreme irradiation, high mass, and detailed observations make HAT P7b a benchmark for understanding hot Jupiter atmospheres. Most massive hot Jupiters resist inflation. Their strong self-gravity compresses them. Yet HAT P7b at 1.78 Jupiter masses is significantly inflated. Something is preventing gravitational collapse. HAT P7b receives such intense stellar irradiation, 1,500 times Jupiter's flux, that even with strong gravity, heating mechanisms are highly efficient. Stellar energy absorbed in the atmosphere is somehow transported deep into the interior, heating it from within and preventing efficient cooling. The exact mechanisms, ohmic dissipation, kinetic energy deposition, tidal heating, are likely all operating. HAT P7b shows that with sufficient irradiation, even massive planets can be significantly inflated. For nearly 4 years, Kepler stared at HAT P7 without blinking. Every 30 minutes, it measured the star's brightness with parts per million precision. The result: Over 800 transits, over 800 eclipses, and continuous phase curve observations revealing the planet's atmospheric dynamics in extraordinary detail. The Kepler dataset for HAT P7b is extraordinary. We can measure brightness variations at the 100 parts per million level continuously for years. This reveals not just average properties, but temporal variability, weather patterns, atmospheric dynamics evolving on timescales of days to months. No ground-based campaign could achieve this. HAT P7b became a natural laboratory for studying hot Jupiter atmospheres in ways impossible with any other planet. As HAT P7b orbits, the amount of planet we see changes. At secondary eclipse, the planet passes behind the star, we see none of it. At transit, it passes in front. We see only its silhouette. Between these, we see varying amounts of the illuminated day side and dark night side. By measuring brightness throughout the orbit, astronomers can map temperature distribution across the planet's surface. Key phase curve findings. Peak brightness offset. The planet is brightest not when directly facing us. As expected, if hottest point is the substellar point, but when offset by about 40 degrees eastward. This reveals that the atmospheric hotspot is shifted eastward from the substellar point by powerful winds. Day-night temperature contrast. Dayside temperature approximately 2,500 to 2,800 K. Nightside approximately 1,400 to 1,700 K. Large contrast indicates relatively inefficient heat redistribution. Strong winds exist but don't perfectly homogenize temperatures. Temporal variability. The brightness varies not just with orbital phase, but also from orbit to orbit. The peak brightness location shifts. The day-night contrast changes. This reveals dynamic weather, clouds forming, dissipating, moving across the planet on timescales of hours to days. The eastward hotspot offset tells us about atmospheric circulation. Supersonic eastward jet streams, 4 to 6 kilometers per second, transport heat from the substellar point before it can radiate to space. By the time air parcels reach maximum temperature, they've been advected eastward, creating the observed offset. The variability tells us weather is happening. Atmospheric patterns evolving faster than the 2.2-day orbital period. In 2016, a team of astronomers analyzed Kepler's phase curves of HAT P7b with unprecedented detail, focusing on the temporal variability. What they found was remarkable. We noticed that the phase curve shape changes over time. Sometimes the planet appears brighter on the night side than expected. Sometimes the day-night contrast is sharper, sometimes smoother. This variability is consistent with clouds, high-altitude reflective clouds on the night side that catch starlight and reflect it to us, making the night side brighter than it would be without clouds. And at HAT P7b's extreme temperatures, we know what those clouds must be made of: corundum, aluminum oxide. Corundum. On Earth, this mineral forms rubies when it contains chromium impurities and sapphires when it contains titanium and iron. On HAT P7b, at temperatures of 1,800 to 2,000 K on the night side, aluminum and oxygen combine to form aluminum oxide, corundum, which condenses into tiny crystals that form exotic clouds. HAT P7b's corundum clouds don't stay in one place. Atmospheric circulation creates a dynamic weather cycle. The corundum cloud cycle. 1. Night-side formation. On the night side, temperatures cool, low enough for aluminum oxide to condense from vapor into solid crystals. Clouds form at high altitudes. 2. Reflectivity. The corundum crystals are highly reflective. They scatter starlight efficiently. When clouds are present on the night side limb, the planet appears brighter than expected in phase curves. 3. Westward transport. While dominant winds are eastward, return flows at different altitudes transport corundum clouds westward, bringing them from the night side toward the day side. 4. Day side evaporation. As clouds reach the hot day side, corundum vaporizes back into aluminum and oxygen atoms. The cycle begins again. 5. Temporal variability. The balance between formation, transport, and evaporation creates variable cloud coverage. Sometimes extensive night-side clouds exist. Sometimes they're transported to the day side and evaporate before new ones form. This creates the observed brightness variability. This is genuine alien weather. On Earth, water evaporates from oceans, forms clouds, rains out, and the cycle repeats. On HAT, P7b, aluminum vaporizes on the day side, flows to the night side where it oxidizes and condenses into corundum clouds, which then get transported back to the day side where they evaporate. It's the same physical principles, evaporation, condensation, transport, but with exotic materials at extreme temperatures. While Kepler's phase curves revealed atmospheric dynamics, spectroscopic observations were needed to determine atmospheric composition. We used ground-based telescopes and Hubble Space Telescope to obtain transmission spectra, measuring how HAT P7b's atmosphere absorbs starlight at different wavelengths during transits. The observations revealed several atmospheric constituents despite the planet's extreme temperature. Observations have detected or inferred multiple atmospheric species on HAT P7b. Key atmospheric detections. Sodium. Strong detection in optical spectrum. At 2200 K, sodium exists as atomic vapor. The broad wings of the sodium absorption lines indicate high atmospheric temperature and pressure broadening. Potassium. Detected at lower amplitude than sodium, but still significant. Both alkali metals are important opacity sources at these temperatures. Water vapor. Evidence for water absorption features in the near-infrared, though water is partially dissociated at the extreme day-side temperatures. More stable on the cooler night side. Hydrogen and helium. Dominant atmospheric constituents, as expected, inferred from mean molecular weight and atmospheric scale height. Titanium oxide and vanadium oxide. Expected to be present based on temperature and possibly responsible for the strong absorption in the optical that creates the temperature inversion. Aluminum oxide. Inferred from cloud observations rather than direct spectroscopic detection. Forms clouds on night side, vaporized on day side. Carbon monoxide. Expected based on equilibrium chemistry at 2200 K. Likely one of the most abundant molecules after H2. One of HAT P7b's most significant features is a temperature inversion, a layer where temperature increases with altitude rather than decreasing. Temperature inversions are created when molecules high in the atmosphere absorb optical and UV radiation from the star, heating that layer. For HAT P7b, titanium oxide and vanadium oxide are the leading candidates. These molecules absorb strongly in the optical and UV, and at 2200 K, they can exist in the observable atmosphere. The inversion affects everything: chemical equilibrium, cloud formation, atmospheric dynamics. HAT P7b's atmosphere is in constant, violent motion, driven by extreme stellar heating and tidal locking. Our circulation models predict dominant eastward equatorial jet streams reaching 5 to 7 kilometers per second, well above the speed of sound in the atmosphere. These jets transport heat, chemical species, and clouds from the day side toward the night side and back through return flows. The hotspot offset observed in phase curves, 40 degrees eastward, directly confirms these supersonic winds. Vertical motions are also strong. Updrafts on the day side rising kilometers in minutes, downdrafts on the night side. The 1000 plus Kelvin temperature difference between day and night creates radically different chemistry on each hemisphere. The day side, most molecules dissociated into atoms. The night side, molecules can reform, water, CO, possibly metal oxides. The rapid circulation, wins completing a circuit in less than the 2.2-day orbital period, transports gas between these chemical regimes faster than chemistry can equilibrate. This creates chemical disequilibrium throughout the atmosphere. We observe molecular abundances that don't match local thermochemical equilibrium because material is transported faster than reactions can proceed. Combining all observations, phase curves, spectroscopy, theoretical models, astronomers have created the most detailed three-dimensional weather map of any hot Jupiter. Key features: equatorial jet stream, dominant eastward flow at 5 to 7 km/s, strongest at equator, transporting heat and materials. Hotspot, located 40 degrees east of substellar point, temperature 800 K, driven by wind advection. Corundum cloud layer, forms on night side at 1,700 to 1,900 K altitude level, covers variable fraction of night side, highly reflective. Day-night transition zones, sharp temperature gradients at terminators, day-night boundaries, strong vertical mixing, complex chemistry. Polar circulation, weaker than equatorial flow but present, creating complex global circulation pattern. Temporal variability, weather patterns evolve on hourly to daily timescales. Cloud coverage varies by factors of 2 to 3, brightness variations detectable from Earth. HAT P7b has become a benchmark for understanding hot Jupiter atmospheres, the standard against which theoretical models are tested. HAT P7b is unique in having 4 years of continuous Kepler observations showing detailed phase curves, spectroscopic detections of multiple species, evidence for exotic clouds, measured temperature inversion, and temporal variability. No other hot Jupiter has this comprehensive dataset. Atmospheric models must reproduce HAT P7b's observed properties, hotspot offset, day-night contrast, cloud variability, to be considered successful. It's become the gold standard. HAT P7b's corundum clouds open scientists' eyes to the diversity of cloud compositions possible on hot Jupiters. HAT P7b sits in the temperature range where corundum clouds form. Not too hot for them to vaporize completely, not too cool for other species to dominate. This makes it perfect for studying this specific exotic cloud chemistry. Understanding corundum cloud formation, transport, and optical properties on HAT P7b helps us predict cloud properties on other planets in similar temperature regimes. Despite extensive study, HAT P7b continues to yield new insights with each new generation of observatories. JWST observations, ongoing. High-resolution spectroscopy, detecting molecules definitively. Eclipse spectroscopy, mapping dayside temperature at multiple wavelengths. Search for additional chemical species. Refine cloud properties and composition. Measure atmospheric metallicity and elemental abundances. Ground-based high-resolution spectroscopy. YELTs, measuring Doppler-shifted molecular lines. Direct wind velocity measurements, confirming circulation models. Time-resolved spectroscopy, tracking atmospheric changes. Detecting the corundum clouds spectroscopically, if possible. Long-term monitoring. Continued phase curve observations, tracking weather evolution. Multi-year campaigns, revealing long-term variability. Comparison to theoretical predictions of climate evolution. 1,040 light-years from Earth, HAT P7b continues its rapid orbit. Every 52.9 hours, every 2.2 days, it completes another circuit around its hot, massive star. One hemisphere eternally bakes under intense radiation. The other faces perpetual night, cooler but still far hotter than any furnace on Earth. Imagine, if such a thing were possible, approaching this world. The day side glows white-hot, thermal radiation intense enough to be visible to the human eye. The star dominates the sky, enormous and blazing. The atmosphere churns with supersonic winds, temperatures climbing to 2,800 Kelvin at the hotspot. But look toward the night side. There, high in the atmosphere, clouds form. Not water clouds, not ammonia or methane like Jupiter's. These are clouds of corundum, aluminum oxide crystals, each one chemically identical to sapphire or ruby. They drift westward, reflecting dim starlight, shimmering against the darkness. As you watch, the weather changes. More clouds form. Winds strengthen and weaken. The hotspot shifts slightly. In hours, the atmospheric pattern has evolved, weather happening not over days or weeks as on Earth, but in the time it takes to watch a movie. Descending deeper, the atmosphere thickens, pressurizes, temperature climbs. Thousands of kilometers down, hydrogen transitions from gas to liquid, then to exotic metallic states. And somewhere far below, perhaps, lies a core of rock and ice, the seed around which this massive planet formed. HAT P7b has taught us that planetary atmospheres can be far more exotic than we imagined. Clouds made of vaporized rock, winds faster than sound, weather patterns visible from over 1,000 light-years away, temperature inversions created by metal oxide absorption. It has become a Rosetta Stone for hot Jupiter science, the planet whose comprehensive observations allow us to test theories, calibrate models, and understand atmospheric processes at extreme temperatures. Every new hot Jupiter discovered is compared to HAT P7b. Every theoretical model is validated against its observations. HAT P7b reminds us that the universe contains phenomena beyond our everyday experience. That planets can have clouds made of materials that on Earth are precious gems. That weather can happen at hypersonic speeds. That atmospheric processes we thought we understood have exotic analogs in alien environments. This is HAT P7b, the sapphire world. A hot Jupiter where clouds form from aluminum oxide, corundum, the mineral of sapphires and rubies. A planet with weather patterns so dynamic they change on timescales of hours. A world observed so thoroughly it has become the benchmark for understanding hot Jupiter atmospheres everywhere. A reminder that the cosmos is filled with wonders stranger than fiction, that clouds can be made of jewels, and that understanding these alien worlds helps us comprehend the fundamental physics and chemistry that shape all planets throughout the universe. The observations continue, the weather evolves, and through the jeweled sky of HAT P7b, we see the diversity and complexity of worlds beyond our solar system. For our next planet, we're warping over to K2-148b and the hopeful search for habitable super-Earths. In the waning months of NASA's Kepler mission, a spacecraft that revolutionized our understanding of planets beyond our solar system, astronomers discovered a world that would become one of the mission's most intriguing finds. K2-148b, a super-Earth orbiting a cool red dwarf star just 280 light-years away, positioned within the habitable zone where temperatures could allow liquid water to exist. The planet is roughly 1.6 times Earth's radius, larger than our world but smaller than Neptune. Its orbit takes just under 18 days, bringing it close to its dim star, yet receiving a stellar flux similar to Earth's. K2-148b represents exactly the kind of world astrobiologists hope might harbor life, a rocky super-Earth in the habitable zone of a nearby, stable M-dwarf. But K2-148b also embodies the challenges of assessing habitability. We know its size and orbit. We can estimate its temperature, but we don't know its mass precisely, its density, or whether it has an atmosphere. Is it a rocky world with oceans beneath clouds? A barren rock stripped of atmosphere? A mini Neptune with no solid surface? This is the story of a discovery made in the mission's final days. A world that offers both promise and mystery, reminding us that finding potentially habitable planets is just the first step in a much longer journey. By 2017, Kepler had been operating for over 8 years. After losing 2 reaction wheels in 2013, engineers devised the K2 mission, using solar pressure to stabilize the spacecraft, observing new fields every 80 days. Campaign 15 was among the final campaigns before Kepler's fuel would run out in October 2018. Campaign 15 observed approximately 23,000 target stars from August to November 2017. K2-148, also cataloged as EPIC 2-4788-7989, was a magnitude 12.8 M dwarf selected as a target because of its proximity and suitability for planet searches. During the 80-day campaign, the automated pipeline detected periodic transit signals every 17.96 days with a depth of about 0.17%, indicating a planet roughly 1.6 Earth radii in size, transiting from our perspective. The transit depth was small, less than 0.2%, requiring careful analysis to distinguish from stellar variability and instrumental noise. But the signal's regularity and consistency marked it as a genuine planetary candidate. Validating K2-148b, confirming it as a genuine planet rather than a false positive, required extensive analysis and follow-up observations. We used multiple validation techniques. High-resolution imaging with adaptive optics at Palomar and Keck observatories ruled out nearby stellar companions that could create false positive transit signals. Spectroscopic analysis characterized the host star's properties: mass, radius, temperature, metallicity. Statistical validation algorithms calculated the probability of false positive scenarios, eclipsing binaries, background eclipsing stars, and found them negligibly small. By 2019, we had validated K2-148b as a genuine super-Earth in the habitable zone. The discovery was announced in 2019 as part of a larger catalog of K2 planets. K2-148b joined the growing list of potentially habitable super-Earths around nearby M dwarfs, planets that might, just might, harbor the conditions for life. K2-148 is an M dwarf, a red dwarf star, the most common type in the galaxy and increasingly recognized as promising hosts for habitable planets. K2-148 is a typical M3 dwarf, small, cool, and dim. Its moderate activity level is encouraging for habitability. Very young M dwarfs produce intense flares that could strip planetary atmospheres, but K2-148 has matured past that phase. Its planets have had billions of years to develop stable atmospheres and potentially life. And at 280 light-years, it's close enough that future telescopes might characterize planetary atmospheres, despite the challenges of non-transiting follow-up. The habitable zone, where liquid water could exist on a planet's surface, depends on how much energy a star radiates. For dim M dwarfs like K2-148, the habitable zone is much closer to the star than Earth is to the Sun. For K2-148, with only 2.4% of the Sun's luminosity, the habitable zone extends roughly from 0.08 to 0.19 AU, much closer than Earth's 1 AU distance from the Sun. K2-148b orbits at approximately 0.127 AU with an 18-day period, placing it comfortably within the habitable zone. The planet receives approximately 1.0 to 1.2 times the stellar flux Earth receives from the Sun, very Earth-like energy input, which is extremely promising for potential habitability. K2-148b's position within the habitable zone is nearly ideal, not at the hot inner edge where runaway greenhouse effects threaten, nor at the cold outer edge where planets risk freezing. It sits in what some call the sweet spot, the most favorable region for temperate surface conditions. From K2 transit observations, astronomers can determine several properties of K2-148b, though important characteristics remain uncertain. K2-148b sits right at the boundary, 1.6 Earth radii, between planets that are likely predominantly rocky and those that might have substantial volatile envelopes. Statistically, planets this size could go either way. Some are rocky super-Earths with at most thin atmospheres. Others are mini-Neptunes with thick hydrogen-helium envelopes and no accessible solid surface. Without a mass measurement, we can't definitively determine which K2-148b is. K2-148b's radius of 1.6 Earth radii places it precisely at one of the most important transitions in planetary science, the Radius Valley. The Radius Valley, also called the Fulton Gap, is a dearth of planets between 1.5 and 2.0 Earth radii. Below this gap, planets are predominantly rocky super-Earths. Above it, they're mini-Neptunes with thick gas envelopes. The valley exists because atmospheric escape, planets losing their gas envelopes to stellar radiation, creates two distinct populations. K2-148b at 1.6 Earth radii sits right at the transition. It could be a large rocky planet that retained a thin atmosphere or a small volatile-rich planet. This ambiguity makes K2-148b both scientifically valuable and frustrating. It's exactly the kind of planet where mass measurements become crucial for understanding its nature and assessing habitability. Without a mass measurement, scientists can only model K2-148b's possible compositions based on its radius and other known planets. Scenario 1. Rocky super-Earth with thin atmosphere. Potentially habitable. Rocky surface, moderate atmosphere. Scenario 2. Water world. Potentially habitable if pressure/temperature allow liquid ocean. Scenario 3. Mini-Neptune. Unlikely to be habitable. No surface, extreme atmospheric conditions. All three scenarios are plausible given the radius alone. Mass measurements would immediately distinguish between them. Rocky super-Earths are denser than water worlds, which are denser than mini-Neptunes. Until we have radial velocity data measuring K2-148b's mass, its true nature remains uncertain. But its location in the habitable zone and moderate stellar flux makes scenarios 1 and 2, rocky or water world, more appealing from a habitability perspective. Despite uncertainties, K2-148b shows several characteristics favorable for potential habitability. Positive habitability factors. Optimal habitable zone position. Receives 1.0-1.2 times Earth's stellar flux, nearly identical to Earth's energy input. This Goldilocks radiation level is ideal for temperate surface conditions. Super-Earth size. At 1.6 Earth radii, large enough to retain atmosphere through strong gravity, but not so large that thick H/He envelope is inevitable. Mature, relatively quiet star. K2-148 is 3 to 7 billion years old, stable, with reduced flaring compared to younger M dwarfs. Likely rocky or water-rich. At the Radius Valley boundary, more likely to be rocky or water-rich than purely gaseous. Proximity to Earth. Only 280 light-years, close enough for potential future atmospheric characterization. Short orbital period. 18-day period means frequent transits, easier to accumulate observations for atmospheric studies. K2-148b checks many boxes for habitability. It's in the right place, the right size, around a suitable star. Of course, we don't yet know the critical details: mass, density, atmospheric presence, and composition. But the fundamentals are extremely encouraging. This is exactly the kind of planet we want to study in detail. Despite favorable conditions, K2-148b faces challenges common to all M-dwarf planets, and significant unknowns remain. Habitability challenges. Tidal locking. At 0.127 AU, almost certainly tidally locked. One side always faces star. Creates extreme day-night contrast without sufficient atmosphere to redistribute heat. M-dwarf activity. Even relatively quiet M-dwarfs produce occasional flares. High-energy radiation could erode atmospheres over time, especially early in the star's history. Unknown mass. Without mass, we can't determine density or distinguish between rocky, water, and gaseous compositions. Unknown atmosphere. No atmospheric detection yet. Planet might be airless, have thin atmosphere, or a thick atmosphere. We don't know. Red light photosynthesis. M-dwarf spectrum peaks in near-infrared. Earth-type photosynthesis evolved for visible light. Life would need to adapt. Historical activity. Young M-dwarfs are highly active. K2-148 likely experienced intense flaring in its first billion years, potentially stripping early atmospheres. The biggest unknown is the atmosphere. If K2-148 be retained or developed a substantial atmosphere, nitrogen, oxygen, water vapor, CO2, it could be genuinely habitable despite tidal locking and M-dwarf challenges. If it lost its atmosphere early or never developed one, it's probably barren. We need observations to answer this fundamental question. For decades, tidal locking was considered a deal-breaker for habitability. But modern climate modeling has changed this view. If K2-148b has an atmosphere with surface pressure above about 0.1 bar, 1/10 Earth's pressure, atmospheric circulation can redistribute heat efficiently. Winds transport heat from the permanent day side to the permanent night side, moderating temperatures across the entire planet. Instead of a scorching day side and frozen night side, you get a temperate day side, moderately cool night side, and potentially habitable conditions at the terminator and beyond. On K2-148b, if it has an atmosphere, the star would hang motionless in the sky on the day side. A dim red-orange sun larger than Earth's sun appears, but only giving about 1/5 the brightness. The day side would experience eternal day. The night side, eternal night. At the terminator, the boundary, conditions might be most temperate, with perpetual sunset or sunrise creating unique habitats if life exists. With radius but no mass, K2-148b remains ambiguous. Mass measurements would immediately clarify its composition and habitability potential. What mass would tell us? If mass, 3-4 Earth masses. Rocky super-Earth composition confirmed. Likely iron silicate planet like Earth, but larger. Potentially habitable if atmosphere present. Best case scenario for habitability. If mass, 4-6 Earth masses. Water-rich composition likely. Could be water world with global ocean. Potentially habitable depending on atmosphere pressure and ocean conditions. If mass, 6-8 Earth masses. Mini Neptune with substantial H/E envelope. Unlikely to have solid or liquid surface. Probably not habitable by Earth standards. Measuring K2-148b's mass requires detecting the tiny wobble its gravity creates in the star's motion. A challenging observation for this system. For a super-Earth of 3 to 5 Earth masses around an M-dwarf, the radial velocity semi-amplitude is typically 2 to 4 meters per second, near the precision limit of current spectrographs. K2-148's magnitude, 12.8, is relatively faint, requiring large telescope time for sufficient signal-to-noise. And M-dwarfs show stellar activity, star spots, faculae, that create radial velocity noise mimicking or obscuring planetary signals. We need dozens of precise measurements over months to years to extract the planetary signal reliably. As of current knowledge, published radial velocity measurements of K2-148b are not available. The planet awaits mass determination, a crucial next step in assessing its habitability. Multiple research teams are likely pursuing these observations, and results may emerge in coming years. The ultimate test of K2-148b's habitability is atmospheric characterization, detecting and analyzing its atmosphere, if it has one. K2-148b is a challenging but potentially feasible target for JWST transmission spectroscopy. We need to combine multiple transits to accumulate sufficient signal, perhaps 5 to 10 transits observed over 1 to 2 years. If the planet has a substantial atmosphere with molecules like water vapor, carbon dioxide, or methane, JWST could potentially detect them. If the atmosphere is thin or absent, we'd see a flat, featureless spectrum. Either result would be scientifically valuable. If K2-148b's atmosphere is detectable, specific molecular signatures would reveal its nature and potential habitability. Target molecules and what they'd mean. Water vapor, H2O, indicates presence of water, essential for life as we know it. Abundant in habitable atmospheres, but also on runaway greenhouse worlds like Venus. Carbon dioxide, CO2, common in terrestrial atmospheres, provides greenhouse warming. Abundance indicates volcanic activity or atmospheric chemistry. Methane, CH4, on Earth, mostly biological, produced by life, but can also be geological. Detection intriguing, but not definitive biosignature alone. Oxygen, O2, or ozone, O3. Strong biosignature when present with reduced gases like methane. Oxygen doesn't last long without continuous replenishment, usually requires life. Molecular nitrogen, N2. Difficult to detect directly, but inferred from atmospheric pressure. Common in habitable atmospheres. Disequilibrium chemistry. Combinations of molecules that shouldn't coexist without active replenishment, like oxygen and methane together, suggest biological processes. The real excitement would be detecting a biosignature pair, oxygen with methane, for example. Gases that react together and shouldn't coexist without continuous production. On Earth, life produces both. Finding this combination on K2-148b would be compelling evidence for biological activity, though we need to rule out non-biological sources very carefully. Beyond transmission spectroscopy, other techniques might reveal K2-148b's properties. Thermal phase curves. JWST observing system brightness throughout planet's orbit could detect thermal emission, constraining temperature and heat redistribution even without transits at certain wavelengths. High-resolution spectroscopy. Future extremely large telescopes using Doppler shifts to separate planetary atmospheric absorption from stellar spectrum. Possible, but very challenging for planets this small. Direct imaging, extremely difficult. At 280 light-years, angular separation very small. Would require enormous space telescope with advanced starlight suppression, possible with missions like Habitable Worlds Observatory in 2040s. K2-148b is one of dozens of potentially habitable planets discovered by the K2 mission, a testament to the spacecraft's resilience and the value of extended missions. After losing 2 reaction wheels, many thought Kepler's planet-hunting days were over. But K2 discovered over 500 confirmed planets and thousands of candidates. Among these are several potentially habitable worlds, like K2-148b. The mission's diversity, observing different fields every 80 days, sampled different stellar populations and found planets around nearby stars that Kepler's original field missed. K2-148b shows that even a crippled spacecraft, creatively repurposed, can make discoveries crucial for astrobiology. K2-148b represents the most common planetary environment in the galaxy, a planet orbiting an M-dwarf, the most numerous stellar type. M-dwarfs comprise 75% of all stars in the Milky Way. Nearly every M-dwarf hosts planets, and many have planets in their habitable zones. If M-dwarf planets can be habitable, if challenges like tidal locking and stellar activity don't preclude life, the number of potentially inhabited worlds in the galaxy is enormous. K2-148b is one of hundreds of such planets we've found. Understanding whether it's habitable has implications for billions of similar worlds throughout the galaxy. 280 light-years from Earth, K2-148b continues its orbit. Every 18 days, every 2.5 weeks, it completes another circuit around its small red star. One hemisphere always faces the star, bathed in dim red-orange light. The other faces eternal darkness. What does K2-148b look like? We don't know. Is it a rocky super-Earth with continents and oceans, clouds drifting through a nitrogen atmosphere? Is it a water world, a global ocean hundreds of kilometers deep beneath a steamy sky? Or is it a mini Neptune with no solid surface, just gas and clouds, all the way down to a small core? All are possible. All await discovery. We know K2-148b is real. We know its size, its orbit, its location in the habitable zone. We know it receives nearly Earth-like stellar energy. But we don't know its mass, its density, whether it has an atmosphere, or whether conditions allow liquid water. Within the next decade, we might know. JWST might detect atmospheric features or confirm their absence. Radial velocity observations might measure its mass and density. We might determine whether K2-148b is a promising candidate for hosting life or just another barren rock. K2-148b reminds us that the search for habitable worlds is progressing step by step. We've found thousands of planets. We've identified hundreds in habitable zones. Now we're beginning to characterize them, to move from we found a planet to we understand what kind of planet it is. K2-148b was discovered in one of K2's final campaigns, a late gift from a mission that exceeded all expectations. It joins a growing catalog of potentially habitable super-Earths around nearby red dwarfs. Each one is a possibility. Each one might harbor life. Each one waits to reveal its secrets. This is K2-148b, the hopeful discovery, a super-Earth in the habitable zone of a nearby red dwarf, receiving Earth-like stellar energy, possibly rocky, possibly with an atmosphere and oceans. A reminder that potentially habitable worlds exist nearby, waiting to be studied. That the question, are we alone, might be answered by characterizing planets like this one, and that every discovery, even in a mission's final days, brings us closer to understanding our place in the cosmos. The observations continue. The planet orbits on, and someday, perhaps soon, we will know what kind of world K2-148b truly is and whether it harbors the conditions for life. I hope you like Star Wars, because next, we're looking at the Tatooine world, Kepler 16b, and the discovery of real circumbinary planets. September 15th, 2011. NASA announced a discovery that seemed straight out of Star Wars. Kepler 16b, a Saturn-sized gas giant 245 light-years from Earth, orbiting not one star but two. A circumbinary planet where sunsets are double, where the gravitational dynamics are mind-bendingly complex, and where the very existence of the planet challenges our theories of how worlds form. Before Kepler 16b, circumbinary planets were theoretical curiosities. Most scientists doubted planets could form in the chaotic environment of a close binary star system, where gravitational perturbations would prevent material from settling into stable orbits long enough to build planets. Yet here was proof, definitive observational proof, that nature is more creative than we imagined. Kepler 16b became instantly famous as the real Tatooine, named after Luke Skywalker's fictional homeworld with its iconic double sunset. But beyond the pop culture appeal, this planet represents a scientific milestone, the first confirmed member of an entirely new class of planets, proving that binary star systems, half of all stellar systems in the galaxy, can harbor worlds. The implications for planetary diversity, formation theories, and the prevalence of planets throughout the universe are profound. NASA's Kepler mission, launched in March 2009, revolutionized exoplanet science by staring at the same patch of sky for years, detecting the tiny brightness dips when planets cross in front of their stars. Among Kepler's 150,000 target stars was Kepler 16, cataloged as KIC 126444769, a moderately bright, eclipsing binary star system 245 light-years away. Kepler 16 was already interesting as an eclipsing binary, two stars orbiting each other close enough that from Earth, each periodically eclipses the other, causing regular brightness dips every 41 days. These eclipses made the system ideal for precise characterization. But in 2010, we noticed something unexpected: additional, tiny brightness dips that couldn't be explained by the binary eclipses alone. These extra transits occurred at irregular intervals, sometimes after 228 days, sometimes 267 days. This irregularity was the signature of a circumbinary planet. In a normal planetary system, transits occur at perfectly regular intervals. Every orbital period, the planet crosses the star at the same time. But Kepler 16b orbits both stars, which themselves are moving. The planet's transits occur at varying intervals because the orientation of the binary system changes relative to Earth over time. Kepler 16b's orbital plane is slightly misaligned with the binary's orbital plane, about 0.5 degrees difference. This means the planet doesn't always transit from our perspective. Sometimes the geometry is favorable and we see transits. Other times the planet passes above or below the binary, as seen from Earth. The transit timing and intervals depend on the complex three-body dynamics, the two stars orbiting each other and the planet orbiting both. This complexity was actually the smoking gun that proved we were seeing a circumbinary planet. Mathematical modeling of these irregular transits allowed astronomers to determine not just the planet's size and orbit, but the entire system architecture with exquisite precision. The discovery was announced in September 2011, making global headlines as the first definitively confirmed circumbinary planet. Kepler 16 consists of two stars locked in a close binary orbit, dancing around their common center of mass every 41 days. The two stars orbit their common center of mass, called the barycenter, which lies between them but closer to the more massive primary star. From the planet's perspective, the two stars spiral around each other in the sky, changing positions relative to each other throughout their 41-day orbit. Sometimes they're side by side at sunset. Sometimes one is rising while the other is setting. The dance is complex and ever-changing. For a planet to orbit both stars in a binary system, what astronomers call a circumbinary or P-type orbit, it must be far enough out that the gravitational influences from both stars combine rather than compete destructively. There's a critical distance inside which orbits are unstable due to competing gravitational pulls from the two stars. For Kepler 16, this critical distance is approximately 0.5 AU. Any planet closer than this would experience chaotic perturbations that would eventually eject it from the system or cause a collision. Kepler 16b orbits at 0.7 AU, safely beyond this critical distance, in what we call the dynamically stable zone. It's stable for billions of years despite the complex gravitational environment. Kepler 16b is a gas giant similar in size to Saturn, but with nearly Jupiter's mass, a dense world orbiting in the habitable zone of its binary star system. Kepler 16b is fascinating because despite its complex orbital environment, it's remarkably similar to Saturn in our solar system. Similar mass, similar size, likely similar composition. But it orbits in a fundamentally different environment. Instead of one sun providing steady illumination, it receives variable radiation from two stars at different temperatures and distances. The seasonal variations in climate dynamics would be extraordinarily complex. Narrator: despite orbiting two stars, Kepler 16b is cold. Much colder than Earth, comparable to Jupiter's temperature. Why so cold? Low combined stellar luminosity. Together, Kepler 16a and 16b produce only 19% of the Sun's luminosity. Even though Kepler 16b orbits at 0.7 AU, closer than Earth's 1 AU, it receives far less energy. Stellar flux receives approximately 0.26 times Earth's solar flux. For comparison, Jupiter at 5.2 AU receives 0.04 times Earth's flux. Kepler 16b receives more than Jupiter but far less than Earth. Equilibrium temperature: approximately 180 to 200 K, depending on albedo and atmospheric heat redistribution. This is similar to Jupiter's 125 K and Saturn's 95 K, but warmer due to closer orbit. At these temperatures, Kepler 16b's atmosphere would be frigid. Any water would be frozen solid. Methane and ammonia, major components of gas giant atmospheres, would form clouds and possibly rain or snow. The planet's appearance might be similar to Saturn's, hazy, with cloud bands and possibly a ring system, though none has been detected. Ironically, Kepler 16b orbits within the binary system's habitable zone, the region where a rocky planet with the right atmosphere could have liquid water. But as a gas giant with no solid surface and frigid temperatures, Kepler 16b itself is not habitable by Earth standards. The habitable zone for Kepler 16 extends from about 0.5 to 1.0 AU, and Kepler 16b at 0.7 AU sits right in the middle. If Kepler 16b were rocky and had a thick atmosphere with greenhouse gases, liquid water could exist. But as a gas giant, it's uninhabitable. However, and this is intriguing, if Kepler 16b has large moons, those moons might be habitable. We haven't detected any moons, but theoretically, a large moon with its own atmosphere could maintain liquid water despite the cold environment, heated by tidal forces from the planet. The gravitational dynamics of Kepler 16 are extraordinarily complex. 3 bodies, 2 stars, and a planet, all influencing each other, creating a system that seems like it should be chaotic but is actually stable. The classical 3-body problem in physics is famously unsolvable. No general analytical solution exists. But nature finds stable configurations. Kepler 16b's orbit is nearly circular despite the binary's elliptical orbit. The planet's orbital plane is tilted only 0.5 degrees from the binary plane. These properties indicate the system formed in a well-organized disk and evolved smoothly. The planet's orbit precesses, its orientation rotates, on timescales of thousands of years due to gravitational perturbations from the stars, but the orbit itself remains stable. On Kepler 16b, the concept of seasons takes on entirely new complexity. Multiple cycles of variability. Binary orbital cycle. The 2 stars orbit each other every 41 days. From Kepler 16b, their separation in the sky changes. Sometimes they're close together, appearing almost as a single bright source. Other times, they're separated by several degrees, creating distinct shadows and illumination patterns. Planetary orbital cycle. Kepler 16b's year is 229 days. During this time, the distance to the binary changes, creating seasonal variations in total received energy, though the orbit is nearly circular, minimizing this effect. Combined effect. The interaction of these cycles creates complex patterns. Sometimes both stars are visible in the same hemisphere of the planet. Other times they're on opposite sides. The total illumination varies by about 30%, depending on the star's positions relative to each other and the planet. If Kepler 16b had seasons like Earth, driven by axial tilt, they would be modulated by these multiple cycles. The climate modeling would be phenomenally complex. Any atmosphere would experience variable heating patterns depending on whether both stars are illuminating one hemisphere or they're separated. Wind patterns, temperature gradients, and atmospheric circulation would be unlike anything in our solar system. Imagine standing on Kepler 16b, or more accurately, in a balloon floating in its upper atmosphere, since there's no solid surface. The sky. Two suns dominate. Kepler 16a appears about 60% the size of the sun as seen from Earth, but only gives about 18% of the illumination, orange dim. Kepler 16b appears much smaller, about 20% the size of the sun from Earth, and gives only dim red light, contributing less than 2% of total illumination. Together, they provide about 26% of Earth's solar constant, perpetual twilight. The dance. Every 41 days, the two stars orbit their common center. From the planet, they appear to spiral around a point in the sky. Sometimes they're close, appearing almost merged. Sometimes they're separated by 10 to 15 degrees. Their dance is hypnotic, ever-changing. Shadows. When both stars are above the horizon, objects cast two distinct shadows, one from each star. The shadows move independently as the stars move. When the stars are close together, shadows nearly overlap. When separated, shadows diverge. Eclipses. Several times per planetary year, from some locations on Kepler 16b, one star eclipses the other, creating spectacular celestial events where one sun passes in front of the other. Before Kepler 16b, many scientists doubted that planets could form in close binary systems. The reasons were compelling. Planet formation requires a protoplanetary disk where dust grains collide, stick together, and gradually build larger bodies. In a binary system, especially a close one like Kepler 16, the two stars' gravity creates strong tidal forces that stir up the disk, potentially preventing material from settling into stable orbits. Gravitational perturbations could eject planetesimals before they grow large. Many models predicted that circumbinary planet formation would be extremely difficult, if not impossible. Kepler 16b's existence proved those models incomplete. Nature found a way. The discovery of Kepler 16b and subsequent circumbinary planets forced revision of formation theories. Modern understanding. Disk formation. A circumbinary disk forms around both stars, extending outward from beyond the critical stability distance. Material in this disk is gravitationally torqued by the binary, but can maintain relatively stable orbits in a ring-like structure. Inner clearing. Tidal forces from the binary clear out material close to the stars, creating an inner cavity. This is why Kepler 16b orbits at 0.7 AU, just beyond where stable circumbinary orbits become possible. Planetesimal growth. Beyond the critical distance, planetesimals can form and grow despite gravitational perturbations. The process is similar to single-star systems, but requires more time and possibly more initial material. Gas accretion. Once a planetary core reaches several Earth masses, it can begin accreting gas from the disk, growing into a gas giant like Kepler 16b. Orbital evolution. Interactions with the remaining disk material caused the planet to migrate. Kepler 16b likely formed farther out and migrated inward to its current position, stopping near the inner edge of the stable zone. Kepler 16b's nearly circular orbit and small inclination suggest it formed in a well-organized circumbinary disk and didn't experience violent gravitational scattering. The system is remarkably orderly despite the complex dynamics. This tells us that nature can create stable, long-lived planetary systems even in environments we once thought hostile to planet formation. Kepler 16b was the first but not the last. Within a year of its announcement, Kepler discovered additional circumbinary planets, confirming that Tatooine worlds are not rare anomalies, but a genuine class of planets. The discovery of multiple circumbinary planets proved Kepler 16b wasn't a fluke. Roughly 5 to 10% of close binary stars might host planets. Given that half of all Sun-like stars are in binary systems, this means circumbinary planets could represent a significant fraction, perhaps 5%, of all planetary systems in the galaxy. That's billions of potential Tatooine worlds in the Milky Way alone. Circumbinary planets discovered so far share several characteristics that reveal constraints on their formation and evolution. Common properties. 1. All are gas giants or large subneptunes. No Earth-sized circumbinary planets have been confirmed yet. This might be observational bias, large planets easier to detect, or might indicate small rocky planets form less readily in binary systems. 2. Most orbit near inner stability boundary. They orbit just beyond the critical distance where orbits become stable. This suggests inward migration stopped at this natural barrier. 3. Nearly circular coplanar orbits. Most have low eccentricity and small inclination relative to the binary plane, indicating formation in organized disks rather than chaotic capture. 4. Many are cold. Because they orbit beyond the instability radius in systems with moderate to low luminosity, they tend to be cold worlds despite orbiting two stars. The tantalizing question remains, could a rocky, temperate circumbinary planet exist in the habitable zone of a binary star system? Kepler 47c, the outermost planet in the Kepler 47 system, orbits at 0.99 AU in its binary's habitable zone. It's a Neptune-sized gas giant, not habitable itself, but it proves planets can form and remain stable in circumbinary habitable zones. If rocky planets can form there, and there's no fundamental reason they can't, potentially habitable circumbinary planets could exist. We just haven't detected one yet, possibly because they're too small for our current instruments. When NASA announced Kepler 16b in September 2011, the media immediately dubbed it the real Tatooine, referencing Luke Skywalker's fictional home world from Star Wars with its iconic binary sunset. The comparison captured public imagination worldwide. For the first time, a science fiction concept, planets with two suns, was confirmed as scientific fact. While Tatooine is a desert world and Kepler 16b is a cold gas giant, the fundamental reality is the same. Worlds where two stars share the sky. The public response was extraordinary. People connected with Kepler 16b because of Star Wars. It showed that science fiction can inspire real science, and real science can be as amazing as fiction. The discovery helped communicate that exoplanet science isn't abstract. It's discovering actual worlds, some of which look like places we've imagined. Kepler 16b will remain a target for continued study as new observational capabilities come online. JWST possibilities. While challenging, JWST could potentially detect thermal emission during eclipses when the planet passes behind the binary, constraining atmospheric temperature and possibly detecting molecular features if signal-to-noise is sufficient. Ground-based high-resolution spectroscopy. Future extremely large telescopes might detect reflected starlight or thermal emission, characterizing atmosphere composition. Transit timing variations. Continued monitoring of Kepler-16b's irregular transits could reveal additional planets in the system through gravitational perturbations. Search for moons. Long-term monitoring might detect moons around Kepler-16b through subtle transit timing or duration variations, potentially habitable moons. Direct imaging, challenging. At 245 light-years, direct imaging would require enormous telescopes and advanced starlight suppression, but future missions in the 2040s plus might achieve it. Kepler-16b's legacy extends far beyond a single planet. Key lessons. 1. Binary systems can form planets. Prove that planets aren't restricted to single star systems. Half of all stars are in binaries. Planets could orbit many of them. 2. Nature is more creative than theory. Challenge predictions that circumbinary planets would be rare or impossible. Nature finds ways to form planets in seemingly hostile environments. 3. Planetary diversity is vast. Added an entirely new category to exoplanet taxonomy. Diversity includes not just planetary properties, but system architectures. 4. Formation theories need flexibility. Required revision of planet formation models to account for binary star environments. Improved our understanding of disk dynamics and planet-star interactions. 5. Potentially habitable circumbinary worlds may exist. Kepler-47c in the habitable zone suggests rocky planets could exist there. Binary systems might host habitable worlds. 245 light-years from Earth, Kepler-16b continues its orbit. Every 229 days, every 7.5 months, it completes another circuit around its twin suns. Two stars, locked in their own 41-day dance, provide dim but continuous light to the cold gas giant. Imagine floating in Kepler-16b's upper atmosphere. Above, two suns will across the sky. Kepler-16a, larger and orange, provides most of the light, dim and orange-tinted compared to Earth's Sunday. Kepler-16b, smaller and red, adds faint crimson hues, casting its own subtle shadow alongside its companions. Every 41 days, the two stars complete their mutual orbit. Their dance is visible. They move relative to each other, spiraling around a point between them. Sometimes they're close, appearing almost as one. Sometimes they're separated by 10 degrees, creating distinct shadows and complex illumination. Below, Kepler-16b's atmosphere churns with complex weather patterns. Methane and ammonia clouds drift in the frigid air. Wind systems, driven by variable heating from the moving suns, create jet streams and vortices unlike any in our solar system. Lightning might crackle through the clouds, briefly illuminating the dim landscape. Deep below, thousands of kilometers down, hydrogen transitions from gas to liquid to exotic metallic states under crushing pressure. At the center, perhaps, lies a small rocky or icy core, the original seed around which this massive world formed billions of years ago. September 15th, 2011, the day we discovered that Tatooine worlds are real, that science fiction had become science fact, that planets can orbit two stars in stable, long-lived configurations. Kepler-16b taught us that the universe is more diverse, more creative, more surprising than we imagined. That half of all stellar systems, binary stars, are potential hosts for planets. That billions of worlds might orbit under binary suns. It showed us that science fiction can inspire science, and science can be as wondrous as fiction. That the cosmos contains phenomena that match our imagination and exceed it. That discovering worlds with two suns is just the beginning. This is Kepler-16b, the Tatooine world. a gas giant orbiting two stars in a gravitationally complex dance that remains stable for billions of years. The first confirmed circumbinary planet, proving that such worlds exist and opening our eyes to an entirely new category of planetary systems. A reminder that the universe is full of places we never imagined, that reality often exceeds fiction, and that two suns in the sky, once thought pure fantasy, is astronomical fact on billions of worlds throughout the galaxy. The binary stars continue their dance. The planet orbits on, and in the sky of Kepler, 16b, two suns share the heavens, just as they do on the fictional Tatooine and countless real worlds throughout the cosmos. For our last world today, I hope you have a sweet tooth, because we're tasting the cotton candy planet, WASP 107b, and the mystery of ultra-low density worlds. 212 light-years from Earth, in the constellation Virgo, orbits one of the strangest planets ever discovered, WASP 107b, a gas giant with a radius 94% that of Jupiter, but only 1/10 Jupiter's mass. Its density, 0.13 grams per cubic centimeter. For comparison, styrofoam has a density of 0.03 g/cm superscript 3. Jupiter's density is 1.33 g/cm superscript 3. Earth's is 5.5 g/cm superscript 3. WASP 107b is literally lighter than cotton candy. This planet shouldn't exist according to traditional planet formation models. With such low mass, it shouldn't have been able to gather enough hydrogen and helium from the protoplanetary disk to form such a massive atmosphere. Yet here it is, a world almost as large as Jupiter, but less dense than any gas cloud you could imagine, with an atmosphere so extended that it offers an unprecedented window into gas giant composition and chemistry. WASP 107b has become one of the most studied exoplanets because its low density makes it ideal for atmospheric characterization. Starlight passes through more atmosphere, hundreds of kilometers more, than on typical planets, making molecular features stronger and easier to detect. Recent observations with the James Webb Space Telescope have revealed WASP 107b's atmosphere in unprecedented detail, discovering water vapor, carbon dioxide, methane, sulfur dioxide, and silicate clouds, a treasure trove of information about how gas giants work. The wide-angle search for planets, WASP, had been discovering hot Jupiters for nearly a decade when, in 2013, astronomers analyzing data from Super-WASP South noticed something extraordinary. WASP 107 was cataloged as a magnitude 11.6 star in Virgo. Between 2006 and 2012, Super-WASP South accumulated thousands of observations. The automated pipeline detected periodic transits every 5.7 days with a depth of approximately 2.2%. Enormous for a transiting planet. A 2.2% transit depth typically indicates a planet significantly larger than Jupiter. But initial radial velocity measurements showed something unexpected. The planet's mass was very low, only about 10% of Jupiter's mass. This combination, large size, low mass, was immediately recognized as extraordinary. The discovery was announced in 2017 after extensive follow-up observations confirmed the planet's properties and ruled out false positive scenarios. WASP 107b joined the handful of known super-puff or ultra-low density planets, worlds so puffy and insubstantial they barely hold together under their own gravity. Measuring WASP 107b's mass required careful radial velocity observations over several years. We used multiple spectrographs, HARPs, HIRES, and others to measure the star's wobble induced by the planet's gravity. The challenge was that with such low mass, the radial velocity amplitude is small, only about 15 meters per second, near the precision limit of our instruments. Additionally, stellar activity can create radial velocity variations that mimic or obscure planetary signals. After years of observations and careful analysis to separate stellar noise from the planetary signal, we confirmed a mass of approximately 0.096 Jupiter masses, about 30 Earth masses. With both radius and mass measured, the density calculation was shocking, approximately 0.13 G/cm superscript 3. This made WASP-107b one of the lowest density planets known, a true superpuff that would float in a sufficiently large bathtub, if such a bathtub existed. WASP-107 is a K-type dwarf star, cooler and smaller than the Sun but larger and hotter than red dwarfs. WASP-107's moderate activity is important for atmospheric studies. Stellar variability, star spots rotating in and out of view, flares, affects observations, creating noise we must account for. But the star is bright enough and stable enough that with careful analysis, we can obtain exquisite atmospheric spectra of the planet. The K-dwarf spectrum also has fewer absorption features than hotter stars, making it easier to detect planetary atmospheric features. WASP-107b is not alone. Long-term radial velocity monitoring revealed a second planet in the system, WASP-107c, a more massive companion in a wider orbit. WASP-107c, outer planet. Mass, approximately 1.8 Jupiter masses, much more massive than WASP-107b. Does not transit from Earth's perspective. Gravitationally influences WASP-107b's orbit. The discovery of WASP-107c was significant for understanding WASP-107b's formation. The outer planet's greater mass suggests it formed first in the protoplanetary disk, possibly affecting where and how WASP-107b formed. Gravitational interactions between the planets might have influenced WASP-107b's migration inward and could contribute to maintaining its extremely inflated state through tidal heating from small eccentricity oscillations. WASP-107b is classified as a warm Neptune or ultra-low density gas giant, a planet so puffy that it barely resembles the compact gas giants of our solar system. WASP-107b shouldn't exist according to traditional planet formation models. With only 30 Earth masses, it's barely above the threshold for runaway gas accretion, the point where a planetary core becomes massive enough to rapidly accumulate hydrogen and helium from the disk. Standard models predict that such a low-mass core couldn't gather the enormous gas envelope WASP-107b has. Yet here it is, almost Jupiter's size with 1/10 the mass. Something unusual happened during its formation or evolution. Several mechanisms might explain WASP-107b's extraordinarily low density, though none alone seems sufficient. 1. Low core mass. WASP-107b's core is estimated at only 1 to 5 Earth masses, much smaller than Jupiter's 10-20 Earth mass core. With less gravitational compression, the atmosphere expands more. 2. Late core formation. If the core formed late, when the protoplanetary disk was already dissipating, gas accretion might have been limited to the remaining material, creating a large envelope on a small core. 3. Formation farther out than migration. WASP-107b might have formed at several AU where the disk was cooler and less dense, accumulating a large but low-density envelope, then migrated inward without losing much mass. 4. Tidal heating. The small but non-zero eccentricity, E, is almost equal to 0.06, possibly maintained by the outer planet's gravitational perturbations, causes tidal flexing that generates internal heat, preventing the atmosphere from contracting. 5. Ongoing mass loss. WASP-107b might be losing atmosphere to space at a high rate, up to several hundred million kg per second, constantly evaporating and expanding the remaining gas. WASP 107b likely requires multiple mechanisms working together to maintain its extreme puffiness. The low core mass allows the envelope to expand naturally. Tidal heating from eccentricity adds energy, and the planet might be actively losing mass, with the escaping atmosphere creating an extended, diffuse outer envelope. Understanding which mechanisms dominate is key to understanding ultra-low density planets generally. With such low gravity, only 11% of Earth's, and intense stellar irradiation, WASP 107b is losing atmosphere to space at a prodigious rate. This rapid atmospheric escape means WASP 107b is evolving on observable timescales. Billions of years ago, it might have been even more massive. Billions of years from now, if escape continues, it might contract to become a smaller, denser Neptune-like planet, or even lose most of its envelope to become a rocky super-Earth. WASP 107b became a top priority target for the James Webb Space Telescope because its extreme puffiness makes it ideal for atmospheric characterization. The atmospheric scale height, how much the atmosphere's thickness changes with altitude, is 1,100 kilometers on WASP 107b compared to 27 kilometers on Jupiter. This means starlight passes through vastly more atmosphere during transits. Molecular absorption features are proportionally stronger, about 40 times stronger than on a compact planet of the same mass. Combined with the planet's large size creating deep transits, WASP 107b gives us the strongest possible signal for atmospheric characterization. JWST observations of WASP 107b, published in November 2023, produced one of the most comprehensive exoplanet atmospheric spectra ever obtained. Water vapor, definitively detected with multiple absorption features across near to mid-infrared. Abundance measured precisely, approximately 0.1 to 1% by volume, depending on atmospheric model. Carbon dioxide, clear detection at 4.3 microns. First time CO2 detected on a warm Neptune. Important for understanding carbon chemistry and possible interior processes. Carbon monoxide, detected, though weaker than CO2. The CO/CO2 ratio provides information about atmospheric chemistry and potential disequilibrium processes. Methane, significantly depleted compared to equilibrium expectations. At WASP 107b's temperature, 740 K, methane should be abundant, but it's nearly absent. This depletion is a major mystery. Sulfur dioxide, surprisingly detected. This molecule requires photochemistry, UV radiation breaking apart H2S, hydrogen sulfide, and water, allowing sulfur and oxygen to combine. Detection indicates active atmospheric chemistry driven by stellar radiation. Hydrogen sulfide, tentatively detected. If confirmed, this rotten egg molecule would indicate sulfur-rich interior composition or deep atmospheric processes bringing sulfur up from the planet's interior. Silicate clouds, evidence for high-altitude clouds composed of tiny silicate, rock vapor, particles. These clouds partially obscure the deeper atmosphere, but don't completely flatten the spectrum, like on some planets. Ammonia, not detected, despite being expected. Like methane, ammonia appears depleted, suggesting unusual chemistry or atmospheric mixing bringing ammonia-depleted gas from deep in the planet. The near absence of methane in WASP 107b's atmosphere is one of the most significant findings from JWST observations. At 740 K, thermochemical equilibrium models predict substantial methane, perhaps 0.1 to 1% of the atmosphere. Instead, we detect almost none. This depletion tells us that deep in the planet, where temperatures exceed 2000 K, methane is destroyed, broken down into carbon monoxide and water. Powerful atmospheric mixing, convection, brings this methane-depleted gas up from the hot interior to the observable atmosphere faster than chemical reactions can reform methane. This is direct evidence for vigorous vertical mixing throughout the entire planet. The methane depletion also implies WASP. 107b's core is relatively small and not extremely hot. If the interior were hotter, even more dramatic chemical disequilibrium would be observed. This constrains formation models and interior structure. WASP 107b's atmosphere contains clouds made of vaporized rock, tiny silicate particles formed when rock vapor condenses at specific temperature pressure levels. At WASP 107b's temperature, rocks like magnesium silicate and iron silicate can vaporize deeper in the atmosphere and then condense into tiny solid particles as temperature decreases with altitude. These clouds form at pressures around 0.001 to 0.01 bar, high in the observable atmosphere. The clouds are patchy, not uniformly distributed, allowing us to see through clearer regions to detect molecules below, while the clouds partially mute features where coverage is thicker. WASP 107b's properties: low core mass, methane depletion, vigorous atmospheric mixing, provide crucial constraints on formation scenarios. 1. Formation beyond ice line. Core formed in the cooler outer disk, where ices could condense, but never grew large enough for runaway gas accretion. 2. Limited gas accretion. With only 1 to 5 Earth mass core, gas accretion was slow and limited. Accumulated atmosphere from remaining disk material, but never became Jupiter-sized. 3. Inward migration. Gravitational interactions with the disk or with WASP 107c caused inward migration. The low core mass and large envelope survive migration relatively intact. 4. Ongoing evolution. Current atmospheric escape and tidal heating from the outer planet's gravitational influence maintain the extremely inflated state. Planet is actively evolving. WASP 107b's atmospheric composition rules out certain formation scenarios. The depleted methane indicates the core must be relatively small and not extremely hot. The presence of sulfur compounds suggests a sulfur-rich interior composition. The overall metallicity, enrichment of heavy elements, is moderate, consistent with formation beyond the ice line, but not in an extremely metal-rich environment. These observational constraints are revolutionizing our ability to test planet formation theories. WASP 107b belongs to a rare class of super-puff or ultra-low density planets that challenge our understanding of planetary physics. These super-puffs share common characteristics: low mass, 10-50 Earth masses, large radius, 10 Earth radii, young host stars, 1 to 3 billion years, and orbits in the 5 to 10 day period range. Most seem to be transitional objects, losing mass to evaporation and possibly evolving towards smaller, denser states. WASP 107b likely represents a transitional state in planetary evolution, caught in the act of transforming from one type of planet to another. Past billions of years ago, possibly even more massive and puffy when first formed, might have had 50-plus Earth masses initially. In the present, it's losing 100 to 300 million kg/s to atmospheric escape. Current mass, 30 Earth masses, extraordinarily low density. Future Scenario 1. Continued slow evaporation. Over billions of years, gradually loses hydrogen and helium envelope, contracts and becomes denser. Eventually becomes a smaller Neptune-like planet, 5-10 Earth radii, 0.5 to 1.0 g/cm superscript 3. Future Scenario 2. Rapid evaporation. If escape rate increases or persists long enough, could lose most atmospheric envelope, exposes rocky/icy core, becomes a super-Earth, 2-3 Earth radii, 5 to 6G/cm superscript 3. WASP-107b has become a Rosetta Stone for understanding atmospheric chemistry on worlds intermediate between rocky planets and gas giants. Disequilibrium chemistry. Methane and ammonia depletion demonstrates that vigorous vertical mixing can overpower chemical equilibrium, bringing deep interior gas to observable altitudes. Photochemistry. SO2 detection proves UV-driven photochemistry operates in warm Neptune atmospheres, creating molecules that wouldn't exist in equilibrium. Metallicity measurements. Precise molecular abundances allow calculation of atmospheric metallicity, the enrichment of heavy elements relative to hydrogen. WASP-107b shows moderate enrichment, 5-10 times solar, constraining formation location. Cloud formation. Silicate clouds at high altitudes demonstrate that vaporized rocks can condense in warm Neptune atmospheres, affecting observations and climate. With the most detailed atmospheric observations of any warm Neptune, WASP-107b has become the benchmark for testing theoretical models. Atmospheric models must reproduce WASP-107b's observed spectrum to be considered successful. This includes the methane depletion, SO2 detection, water abundance, cloud properties, and spectral shape. Models that fail to match WASP-107b need refinement. This planet has already exposed weaknesses in previous models. Many predicted more methane, fewer clouds, different CO/CO2 ratios. WASP-107b is forcing us to improve our understanding of atmospheric physics and chemistry. WASP-107b's characteristics provide a template for finding and studying other ultra-low density planets. This includes target selection. Astronomers now prioritize observing warm Neptunes with low densities and bright host stars, expecting similarly rich atmospheric features. Comparative studies. Observing multiple superpuffs reveals whether WASP-107b's properties are typical or unusual. Initial results suggest methane depletion might be common on warm Neptunes. Lastly, population statistics. Understanding what fraction of warm Neptunes are superpuffs helps constrain formation timescales and disk conditions across the galaxy. WASP-107b will remain a top observational priority for years to come. WASP-107b represents a snapshot in planetary evolution, a world caught in the act of transformation. Superpuffs like WASP-107b are probably transitional. They're losing mass, evolving toward denser states. In a billion years, WASP-107b might be significantly different, smaller, denser, with different atmospheric composition. We're lucky to observe it now, at this ephemeral stage. These planets teach us about evolutionary pathways connecting different planet types, from bloated gas giants to compact Neptunes to possibly rocky super-Earths. 212 light-years from Earth, WASP-107b continues its orbit. Every 5.7 days, every 137 hours, it completes another circuit around its orange dwarf star. One hemisphere eternally faces the star. The other knows only darkness. Imagine, if such a thing were possible, descending toward WASP-107b. From space, the planet appears enormous, nearly Jupiter's size. But approaching it, you realize how insubstantial it is. The atmosphere extends far above the surface, though there's no true surface, just gas becoming gradually denser. Entering the upper atmosphere, you float through tenuous hydrogen and helium. Density so low it's barely distinguishable from space. Gravity is gentle, only 11% of Earth's. You drift downward slowly, almost floating. Higher up, silicate clouds drift, tiny rock vapor particles suspended in the thin air. Below the clouds, the atmosphere thickens. Water vapor molecules float past. Carbon dioxide, sulfur dioxide, traces of hydrogen sulfide. The smell, if you could smell, might be faintly sulfurous. Deeper still, pressure mounts. Hydrogen transitions from gas to liquid. Temperature climbs 500 K, 1000 K, 2000 K. Methane molecules that form here are torn apart before they can rise. Carbon monoxide and water dominate the hot depths. Thousands of kilometers down, at the center, lies a small core. Rock and ice, perhaps only a few Earth masses. The seed around which this ephemeral giant formed, now dwarfed by the enormous atmosphere above. WASP 107b has taught us that planets exist in states we never imagined. That worlds can be lighter than cotton candy, yet stable over billions of years. That atmospheres can be so extended they offer unprecedented windows in a chemical composition. It has become the benchmark for warm Neptune atmospheric studies. Every new observation reveals surprises: depleted methane, unexpected sulfur dioxide, vigorous vertical mixing. It has forced revision of formation theories and atmospheric models. WASP 107b reminds us that planets are not static. They form, evolve, change. Some grow denser over time. Some lose mass to evaporation. WASP 107b is in transition, perhaps transforming from a more massive past toward a denser future, caught at this ephemeral stage where it's lighter than air, yet substantial enough to orbit for billions of years. This is WASP 107b, the cotton candy planet, an ultra-low density gas giant with a density of 0.13 g/cm superscript 3, lighter than styrofoam, lighter than clouds. A world whose extended atmosphere revealed water, carbon dioxide, sulfur dioxide, and silicate clouds in unprecedented detail. A planet in transition, evolving before our eyes. A reminder that the cosmos contains phenomena that defy expectations. That planets can be ethereal yet real, puffy yet stable, ephemeral yet ancient. And that by studying these extraordinary worlds, we understand the full range of planetary diversity throughout the universe. The observations are ongoing. The atmosphere escapes. And through WASP 107b's cotton candy clouds, we see the complexity of gas, giant formation, evolution, and chemistry more clearly than ever before. If you made it all the way through this video, thank you so much. It really does mean all the worlds to me. Make sure to like, subscribe, and leave a comment about what exoplanet I should cover in the next video. I'll see you tomorrow, and thank you for watching.